Hello there. You're listening to Science Blanket, your quiet space for wonder. I'm so glad you've joined me tonight. Tonight, we are wrapping ourselves in the great mysteries that science cannot yet explain. We often think of science as a bright lantern, illuminating every corner of our world. But beyond that circle of light lies a vast, velvet darkness, a collection of puzzles that remain unsolved, from the silent origins of consciousness to the invisible forces that stretch across the cosmos. These aren't gaps to be feared, but beautiful, quiet spaces for our imagination to rest. As we begin, imagine yourself standing on the edge of a calm, shoreless sea, looking out into a soft, purple twilight. You don't need to find the answers tonight, and you don't need to solve the impossible. Just let the wonder of the unknown settle over you like a warm, heavy quilt. If this blanket of curiosity helps you find peace, please consider subscribing to the channel. It helps us keep the lights low and the stories flowing for every sleepy mind in our community. Now, take a long, slow breath. Feel the mattress rising up to meet you, supporting every part of your body. Let the muscles in your face soften. Feel your heartbeat slow to a steady, rhythmic pulse, and let go of the need to understand. Give yourself permission to simply exist in the wonder of it all. Let's explore the mysteries of the unknown together. In the quiet hours of night, when the world around us settles into stillness, our minds often drift toward the grandest questions of existence. There are mysteries woven into the very fabric of reality, puzzles that have occupied the greatest scientific minds for generations, and yet they remain tantalizingly beyond our complete understanding. These are not questions of trivial curiosity but fundamental enigmas that touch the deepest nature of everything we know and everything we are. Science has given us remarkable tools to probe the universe, revealing structures of breathtaking complexity and beauty, from the smallest quantum fluctuations to the vast cosmic web stretching across billions of light-years. But even as our knowledge expands, we find ourselves confronting boundaries where our understanding falters, where the equations grow silent, and where nature guards her most profound secrets with an almost playful inscrutability. Perhaps no question strikes more directly at the heart of existence than this simple yet devastating inquiry. Why is there something rather than nothing? It seems almost absurd to ask, standing as we do in a universe brimming with galaxies and stars, planets and life, matter and energy in endless permutations. Yet the question persists because it acknowledges an uncomfortable truth: nothing would have been so much simpler. The absence of existence requires no explanation, no mechanism, no cause. It is the default state, or so our intuition suggests. But here we are, immersed in a cosmos of staggering complexity, and we must wonder what broke the perfect symmetry of non-existence. Physicists have discovered that even empty space is not truly empty. Quantum field theory reveals that what we call a vacuum seethes with activity, with virtual particles flickering in and out of existence, borrowing energy from the universe for infinitesimally brief moments before vanishing again. These quantum vacuum fluctuations demonstrate that nothingness is inherently unstable, that the void itself contains the seeds of creation. Some theorists suggest that our entire universe might have emerged from just such a fluctuation, a moment when the quantum foam gave birth to space and time and matter. Yet this explanation, elegant as it may be, merely pushes the mystery back one level. For we must then ask, why do quantum fields exist? Why do they have the properties they have? Why are there laws of physics at all, laws that permit these fluctuations and govern their behavior? We trade one mystery for another, finding no final resting place for our inquiry, no ultimate foundation upon which everything else is built. The question of why anything exists remains suspended in a philosophical space where science can describe mechanisms but cannot provide the deeper law or principle that explains why those mechanisms themselves should be real. When we lift our eyes to the night sky, we see only a tiny fraction of what exists. The observable universe stretches approximately 46 billion light-years in every direction from Earth, a sphere whose boundary is defined not by any physical edge but by the limitations of light and time. Light travels at a finite speed, and the universe has existed for only a finite duration since the Big Bang, roughly 13.8 billion years. You might expect that the observable universe would therefore extend only 13.8 billion light-years in each direction, but the expansion of space itself has carried distant regions even farther away during the time their light has been traveling toward us. Yet this observable portion is merely a fragment of the whole. The universe extends far beyond what we can see, perhaps infinitely so, its full extent hidden behind a cosmic horizon that we can never breach. We know this because we can measure the geometry of space, its curvature or lack thereof, and we find that the universe appears to be flat or very nearly so. A flat universe that began from a hot dense state necessarily extends far beyond our observable patch. But here we encounter another puzzle, one that has grown more perplexing in recent years. The expansion rate of the universe, quantified by the Hubble constant, has become a source of genuine confusion in cosmology. Different methods of measuring cosmic expansion yield different answers, and the discrepancy is too large to ignore, too persistent to dismiss as mere experimental error. When astronomers observe distant supernovae, exploding stars whose intrinsic brightness is well understood, they can calculate how fast those supernovae are receding from us based on the redshift of their light. This method yields one value for the Hubble constant. But when cosmologists examine the cosmic microwave background, the ancient light left over from the Big Bang that fills all of space with a faint glow, they can infer a different expansion rate based on detailed models of how the early universe evolved. These two values disagree by about 8 to 9%, a gap that has grown more pronounced as measurements have become more precise. This conflict, known as the Hubble tension, suggests that something is missing from our cosmological models. Perhaps there is some exotic form of energy or matter that we have not yet accounted for. Perhaps the expansion rate has not been constant in ways we do not fully understand. Perhaps our models of the early universe require revision. Or perhaps we are witnessing the first hints of physics beyond our current framework, phenomena that require entirely new concepts to explain. The tension remains unresolved, a crack in the edifice of modern cosmology that refuses to close. The cosmic microwave background holds other mysteries as well. This radiation, cooled by cosmic expansion to just a few degrees above absolute zero, carries within its subtle variations a wealth of information about the infant universe. When we map the temperature of this radiation across the sky, we find it remarkably uniform, varying by only 1 part in 100,000 from place to place. This uniformity presents what is called the horizon problem. In the earliest moments after the Big Bang, different regions of space were too far apart for light or any signal to have traveled between them. They were beyond each other's horizons, causally disconnected, unable to influence one another in any way. Yet they somehow ended up at precisely the same temperature, in the same quantum state, as though they had been in contact and equilibrated. How did regions of space that could never have communicated end up so perfectly coordinated? The standard model of the Big Bang offers no natural explanation. One proposed solution is cosmic inflation, a brief period of exponentially rapid expansion in the first fraction of a second after creation. Inflation would have stretched a tiny causally connected patch to scales larger than the observable universe today, explaining the uniformity we see. But inflation itself requires specific conditions and mechanisms that are not fully understood, and it introduces new questions even as it answers old ones. Perhaps even more unsettling is what some cosmologists have dubbed the axis of evil, a curious alignment in the cosmic microwave background that should not exist. When scientists analyze the large-scale patterns in the temperature variations of this ancient radiation, they find that certain features are aligned with the plane of the solar system and the direction of Earth's motion through space. This is deeply strange because the cosmic microwave background originated nearly 14 billion years ago, long before the solar system existed, and should have no relationship whatsoever to our local neighborhood. The alignment could be a statistical fluke, an artifact of how we process the data, or it could point to something fundamentally wrong in our understanding of the universe's structure or our place within it. Multiple studies have examined this anomaly from different angles, and it persists, a strange coincidence that refuses to disappear and offers no clear explanation. Some researchers suggest that it might indicate an unexpected pattern in the fabric of space itself, a violation of the cosmological principle that the universe should look roughly the same in all directions. Others remain skeptical, suspecting that some subtle systematic error must be responsible. But the alignment remains, a cosmic enigma printed across the sky, challenging our assumption that there is nothing special about our location or orientation in the universe. Looking toward the distant future, we confront profound uncertainty about the ultimate fate of everything that exists. The universe has been expanding since its beginning, but will this expansion continue forever, or will gravity eventually halt and reverse it, causing all of space to collapse back into a cosmic crunch? For decades, cosmologists assumed that the matter content of the universe would determine its destiny. If there was enough matter, its gravitational attraction would slow and eventually stop the expansion. If there was too little, the universe would expand forever, growing ever more dilute and cold. But observations over the past few decades have revealed a shocking truth. The expansion is not slowing down at all. It is accelerating. Something is pushing space apart with ever-increasing vigor, something we have named dark energy even though we have no idea what it actually is. This dark energy appears to dominate the universe, comprising roughly 68% of all energy and matter. It behaves like a kind of anti-gravity, inherent in space itself, growing stronger as space expands because its density remains constant even as the universe grows. If dark energy continues to dominate, the universe will expand forever at an accelerating pace, eventually tearing apart galaxy clusters, then galaxies themselves, then stars and planets, and finally atoms, in a scenario called the Big Rip. But we do not truly understand what dark energy is or whether its properties might change over cosmic time. It could be Einstein's cosmological constant, a fixed energy built into the vacuum of space. It could be a dynamic field that evolves, potentially weakening or even reversing its effect in the far future. Without understanding its nature, we cannot confidently predict the ultimate fate of the cosmos. The existence of matter itself presents a profound puzzle. When the universe emerged from the Big Bang, it should have created equal amounts of matter and antimatter, particles, and their mirror opposites that annihilate one another when they meet, converting their mass entirely into energy. If matter and antimatter were truly created in equal quantities, they should have destroyed each other completely, leaving behind only radiation. Yet we live in a universe made almost entirely of matter, with antimatter appearing only briefly in high-energy processes. Something tipped the balance ever so slightly, leaving a tiny excess of matter for every billion matter-antimatter pairs. That small surplus became everything we see today: every star, every planet, every atom in our bodies. We know that the laws of physics allow for a subtle difference between matter and antimatter, a phenomenon called CP violation that has been observed in particle physics experiments. But when we calculate how much matter-antimatter asymmetry this known CP violation can produce, we find it falls short by many orders of magnitude. The CP violation we have measured is simply not enough to explain why matter survived. There must be additional sources of asymmetry, new physics beyond the standard model of particle physics that we have not yet discovered. Perhaps there are exotic processes that occurred in the very early universe, when temperatures and energies were far higher than anything we can recreate in laboratories. Perhaps there are new types of particles or interactions that only manifest under those extreme conditions. The answer remains hidden, leaving us to wonder why we exist at all, why the universe is filled with something rather than being an empty bath of radiation. Even more mysterious is the fact that most of the matter in the universe is not the ordinary matter that makes up stars and planets and ourselves. Observations of galaxy rotation curves, gravitational lensing, and the large-scale structure of the cosmos all indicate that roughly 85% of the matter in the universe does not emit, absorb, or reflect light. This dark matter can be detected only through its gravitational effects, the way it bends space-time and influences the motion of visible matter. We know it must be there because galaxies rotate in ways that cannot be explained by their visible matter alone. The outer edges of spiral galaxies spin so fast that they should fling themselves apart unless there is far more mass present than we can see, a vast halo of invisible material providing the extra gravitational glue. Similarly, when we observe how galaxy clusters bend the light from more distant objects behind them, we find that the lensing effect is far stronger than the visible matter can account for. Dark matter must permeate every galaxy and fill the space between galaxies, forming an invisible scaffolding upon which the visible universe is built. Yet despite decades of increasingly sophisticated experiments, we have not directly detected a single dark matter particle. Underground detectors sitting in quiet darkness, waiting for a rare collision between a dark matter particle and ordinary matter, have come up empty. Particle accelerators smashing protons together at nearly the speed of light, hoping to create dark matter particles, have found nothing definitive. Space-based telescopes searching for the faint glow that might result from dark matter particles annihilating each other have seen no clear signal. We know dark matter exists through its gravitational signature, but its fundamental nature remains a complete mystery. It could be composed of undiscovered subatomic particles, massive and barely interacting with ordinary matter. It could be primordial black holes formed in the earliest moments of the universe. It could be something even stranger, a manifestation of physics we have not yet imagined. The darkness is not merely an absence of light but an absence of understanding, a vast component of reality that remains stubbornly hidden. And yet, even when we account for dark matter, we find that much of the ordinary matter that should exist seems to be missing. Theoretical calculations based on Big Bang nucleosynthesis, the process that created the first light elements in the early universe, tell us how much normal matter should exist: protons, neutrons, electrons, the atoms that make up everything familiar. When we add up all the matter we can see in stars, gas clouds, dust, and all the baryonic matter we can detect through various means, we come up short. Roughly half of the ordinary matter that should exist according to theory cannot be accounted for in observations. This is the missing baryon problem, and for years it baffled astronomers. Where did all that matter go? The most likely explanation is that it resides in a diffuse, hot gas that fills the space between galaxies, too thin and too hot to emit detectable light but present in vast quantities. This warm-hot intergalactic medium has been detected indirectly through its absorption of certain wavelengths of light from distant quasars and through faint X-ray emissions, but mapping its full extent remains a challenge. Much of the universe's ordinary matter apparently drifts in the voids between galaxies, invisible threads in the cosmic web, contributing to the overall mass budget but hidden from casual observation. Even this answer, however, is not entirely satisfying, as the techniques for detecting this material are difficult and the measurements uncertain. We think we know where the missing baryons are, but our view remains incomplete, our census of the cosmos still unfinished. These mysteries are not isolated curiosities but interconnected threads in the tapestry of cosmic understanding. They remind us that despite the remarkable progress of science, despite our ability to trace the universe's history back to fractions of a second after its birth and to map its structure across billions of light-years, we remain humble students of nature, perpetually astonished by what we do not know. The universe is far stranger and more complex than our ancestors imagined, and perhaps stranger than we can yet imagine. Each answer we find seems to illuminate new questions. Each mystery solved reveals others waiting in the shadows. And so we continue to look, to measure, to theorize, driven by an ancient hunger to understand our place in this vast and enigmatic cosmos. As we venture deeper into the cosmos and probe the fundamental laws that govern reality, we encounter phenomena that stretch our understanding to its breaking point. The universe does not simply present us with puzzles to be solved through patient effort and clever technique. Instead, it offers riddles wrapped in paradoxes, events that seem to violate everything we think we know, and theoretical frameworks that refuse to reconcile with one another. These are the mysteries that occupy physicists and astronomers in the small hours, the problems that resist solution not because we lack data but because the data itself seems impossible, because nature appears to be telling us that our most cherished theories are incomplete or perhaps even fundamentally flawed. Among the most perplexing cosmic phenomena discovered in recent years are fast radio bursts, brief but incredibly powerful flashes of radio waves that arrive at Earth from distant galaxies. Each burst lasts only a few milliseconds, a blink in cosmic terms, yet in that fleeting moment a fast radio burst releases as much energy as the sun emits in an entire day. The first such burst was discovered in archival data from 2001, but it was not until several years later that astronomers began to realize these events were not mere instrumental glitches but genuine cosmic phenomena. Since then, hundreds of fast radio bursts have been detected, arriving seemingly at random from various points across the sky. What makes them especially mysterious is their inconsistency. Some fast radio bursts appear once and never repeat, suggesting they might be produced by catastrophic events that destroy their source. Others repeat on irregular schedules, flashing again and again from the same location, implying a more durable mechanism. The distances involved are staggering, with most bursts originating billions of light-years away, which means they must be extraordinarily luminous to be detectable at all. Theories abound regarding their origin. Perhaps they are produced by highly magnetized neutron stars called magnetars, whose intense magnetic fields can trigger explosive releases of energy. Perhaps they result from collisions or interactions between neutron stars and other objects. Perhaps they involve exotic physics we have not yet considered. Some of the repeating bursts show patterns in their timing, hints of periodicity that might suggest orbiting systems or rotating objects. But no single theory accounts for all the observed properties, and the diversity of fast radio burst behavior suggests that multiple mechanisms might be at work. The universe, it seems, has found several ways to produce these brilliant flashes, and we have yet to fully understand any of them. If fast radio bursts challenge our understanding of extreme astrophysics, other cosmic events push even further into the realm of the seemingly impossible. On the 15th of October in 1991, a cosmic ray detector in Utah recorded a single particle arriving from space with an energy so extreme that it defied all expectations. This particle, which came to be known as the Oh My God particle, carried approximately 300 million trillion electron volts of energy. To put this in perspective, it had roughly the same kinetic energy as a baseball thrown at modest speed, except all that energy was concentrated in a single subatomic particle. Such particles should not exist according to our understanding of cosmic acceleration mechanisms. The most powerful particle accelerators we can build on Earth produce energies millions of times lower. Even the most violent events in the universe, supernova explosions, and the environments around supermassive black holes, struggle to explain how a single particle could be accelerated to such an extreme energy. Moreover, particles with such high energies should interact with the cosmic microwave background radiation that fills all of space, losing energy through a process called the GZK cutoff. This effect should limit the maximum energy of cosmic rays arriving at Earth and restrict their sources to our relatively nearby cosmic neighborhood. Yet the Oh My God particle seems to have violated this limit, arriving with energy that suggested either an extremely powerful and relatively nearby source, or some fundamentally new physics that allows particles to travel farther than we think possible. Attempts to trace the particle's trajectory back to its source yielded no obvious candidate. It seemed to come from an empty region of sky with no known energetic object. Since then, a handful of other ultra-high energy cosmic rays have been detected, but they remain exceedingly rare, and their origins remain deeply mysterious. They stand as reminders that the universe contains acceleration mechanisms we do not understand, processes capable of focusing unimaginable amounts of energy into single particles. Not all cosmic mysteries arrive from distant galaxies. Some announce themselves from our own celestial backyard and then vanish before we can properly study them. On the 15th of August in 1977, a radio telescope in Ohio detected a signal so unusual and so powerful that the astronomer reviewing the data wrote "Wow" in the margin of the computer printout. The "Wow" signal lasted 72 seconds, the maximum time the telescope could observe any given point in the sky before Earth's rotation carried it out of view. During those 72 seconds, the signal's intensity rose and fell in a pattern consistent with an extraterrestrial radio source being tracked across the telescope's field of view. What made the signal especially intriguing was its frequency, which fell close to the hydrogen line at 1420 MHz, a frequency that many scientists have proposed as a logical choice for interstellar communication because hydrogen is the most abundant element in the universe and its emission frequency is well known to any technological civilization. The signal's narrowband nature also suggested it was not a natural phenomenon, as most natural radio sources emit across a broad range of frequencies. Yet despite extensive searches, the Wow signal has never repeated. The telescope has pointed at the same region of sky many times since 1977, and other telescopes have joined the search, but that particular signal has never appeared again. Various explanations have been proposed over the decades. Perhaps it was interference from a passing satellite or aircraft, though this seems unlikely given the signal's characteristics and the telescope's design. Perhaps it was a brief flare from a distant star or some exotic astrophysical event. A recent hypothesis suggests it might have been caused by a comet with an unusual hydrogen cloud, though this explanation remains controversial. The truth is we simply do not know. The WOW signal remains one of the most tantalizing hints of something extraordinary, a cosmic whisper that spoke once and fell silent. When astronomers peer to the edges of the observable universe, looking back in time to when the cosmos was young, they find objects that should not yet exist. Supermassive black holes, containing millions or even billions of times the mass of our Sun, appear in observations of the early universe, existing when the cosmos was less than 1 billion years old. These behemoths present a serious challenge to our understanding of how black holes grow. In the standard model of black hole formation, they begin as stellar remnants, the collapsed cores of massive stars that have exploded as supernovae. These stellar mass black holes, typically containing only a few times the Sun's mass, then grow by accreting material from their surroundings or merging with other black holes. But this growth process is relatively slow. There are limits to how quickly a black hole can consume matter because the infalling material heats up and radiates energy, creating pressure that pushes back against further accretion. This is called the Eddington limit, and it suggests that even under ideal conditions, black holes can only grow at a certain maximum rate. When we calculate how long it would take a stellar mass black hole to grow into a billion solar mass monster through steady accretion, we find that the early universe simply did not provide enough time. Either these supermassive black holes had to start much larger than we think possible, perhaps forming directly from the collapse of enormous clouds of primordial gas without going through a stellar phase, or they had to grow faster than the Eddington limit should allow, perhaps through sustained episodes of super-Eddington accretion that we do not fully understand. Neither explanation is entirely satisfying, and both require special conditions that may not have been common in the early universe. Yet there the supermassive black holes sit in our observations, fully formed and ready to power brilliant quasars, existing at a time when they should still be infants. As we probe these cosmic mysteries, we inevitably confront the limitations of our fundamental theories. Physics rests on two great pillars: general relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which governs the behavior of matter and energy at the smallest scales. Both theories have been tested extensively and have passed every experimental challenge thrown at them. Yet they are fundamentally incompatible with each other. General relativity treats space-time as a smooth, continuous fabric that can bend and ripple in response to mass and energy. Quantum mechanics insists that at the smallest scales, everything becomes discrete and probabilistic, governed by wave functions and uncertainty principles. When we try to describe situations where both theories should apply, such as the interior of black holes or the first moments of the Big Bang, the mathematics breaks down. The smooth space-time of general relativity cannot accommodate the quantum fluctuations that must exist at tiny scales. The quantum description of matter cannot properly account for the dynamic, curved space-time of general relativity. This is the problem of quantum gravity, and despite decades of effort, we have no complete solution. String theory proposes that fundamental particles are actually tiny vibrating strings, and that space-time itself has extra dimensions curled up at scales far too small to detect. Loop quantum gravity suggests that space-time is itself quantized, made of discrete chunks at the smallest scales. Other approaches, from causal set theory to asymptotic safety, offer their own frameworks. But none has achieved the status of a confirmed, complete theory. None has made predictions that can be tested with current technology. We find ourselves in the frustrating position of knowing that our two best theories must be approximations to some deeper truth, yet that deeper truth continues to elude us. Black holes themselves, even setting aside the question of quantum gravity, present profound conceptual puzzles. When matter falls into a black hole, it seems to disappear from the universe, crossing the event horizon and becoming forever inaccessible to outside observers. But in the 1970s, Stephen Hawking demonstrated that black holes are not entirely black. Quantum effects near the event horizon cause black holes to emit a faint thermal radiation, slowly losing mass in the process. Given enough time, a black hole will evaporate completely, transforming its mass into this Hawking radiation and leaving nothing behind. This creates what is known as the black hole information paradox. In quantum mechanics, information is never truly lost. The quantum state of a system evolves in a deterministic, reversible way, meaning that in principle, you could always reconstruct the past from the present. But if a black hole can swallow matter and then evaporate, emitting only featureless thermal radiation that carries no information about what fell in, then information has been destroyed. This violates fundamental principles of quantum mechanics. The paradox has sparked intense debate. Some physicists argue that information must be preserved, perhaps encoded in subtle correlations in the Hawking radiation, or perhaps stored in some way at the event horizon. Others suggest that information might truly be lost, requiring a revision of quantum mechanics itself. Recent work on holography and the ADS-CFT correspondence has provided hints that information might be preserved in ways we did not previously understand, but a complete resolution remains elusive. The paradox touches on deep questions about the nature of reality, the relationship between information and physical law, and the limits of what we can know about the universe. Related to this is the question of what black holes actually contain. The no-hair theorem in general relativity states that black holes can be completely described by just three properties: their mass, their electric charge, and their angular momentum or spin. Everything else about the matter that formed the black hole or fell into it, all the complex details of its composition and structure, are supposedly erased, hidden behind the event horizon. The black hole, in this view, has no hair, no distinguishing features beyond those three numbers. But this seems to contradict our intuition that different objects should leave different imprints. If you dropped an encyclopedia into a black hole, and then dropped a star of the same mass, would the resulting black holes really be identical? The no-hair theorem says yes, but this feels like a loss of information, tying back to the information paradox. Some physicists have proposed that black holes might have more structure than the no-hair theorem suggests, perhaps with quantum hair or other subtle features that encode additional information. Others argue that the theorem is essentially correct, but that information is preserved in ways that do not violate it. The debate continues, with black holes serving as theoretical laboratories where our ideas about space-time, quantum mechanics, and information collide. Beyond the mysteries of black holes and cosmology, pure physics presents its own set of unsolved problems, some so fundamental that they have been designated Millennium Prize problems with million-dollar rewards for their solution. One such problem involves Young-Mills theory, a mathematical framework that underlies the standard model of particle physics. Young-Mills theories describe how particles interact through force fields, and they successfully explain the strong nuclear force that holds quarks together inside protons and neutrons. But despite the theory's empirical success, we lack a rigorous mathematical proof that a non-trivial Young-Mills theory with a mass gap actually exists. The mass gap refers to the idea that the particles in the theory have a minimum mass, that there is an energy gap between the vacuum state and the next excited state. We believe this is true based on experimental evidence and numerical calculations, but we cannot prove it mathematically. The problem is not merely academic. Understanding the mathematical foundations of Young-Mills theory would deepen our comprehension of the strong force and might reveal new insights into the nature of quantum field theories in general. But the mathematics involved is extraordinarily difficult, involving deep questions about the behavior of nonlinear differential equations and the structure of quantum field theories. Decades of effort by brilliant mathematicians and physicists have made progress but have not yet achieved a complete proof. Closely related is the phenomenon of color confinement, the observation that quarks and gluons, the fundamental constituents of protons and neutrons, can never be isolated. When you try to pull a quark out of a proton, the energy required grows with distance. Eventually, there is enough energy to create new quark-antiquark pairs from the vacuum, and you end up with multiple bound particles rather than a free quark. This is why we never observe isolated quarks in nature, only composite particles like protons and mesons where quarks are bound together. We have ample experimental confirmation that confinement is real, and we have strong numerical evidence from lattice QCD calculations that the theory of quantum chromodynamics indeed produces confinement. But we lack an analytic proof, a demonstration from first principles that the theory must confine quarks. The nonlinear nature of the strong force, where gluons carry color charge and interact with each other as well as with quarks, makes the mathematics extraordinarily complex. Confinement emerges from this complexity, but capturing it in a rigorous proof remains beyond our current mathematical capabilities. It is a humbling reminder that even in areas where we have a working theory that agrees beautifully with experiment, we may not fully understand why the theory works or what its mathematical structure implies. Even seemingly simple questions about light and matter can lead to surprising controversies. When light travels through a material medium like water or glass, it carries momentum, and this momentum can be transferred to the material. But exactly how much momentum light carries in a medium has been the subject of a debate that has persisted for over a century. The Abraham formulation suggests one value for the momentum, while the Minkowski formulation suggests another, and the two differ by a factor related to the refractive index of the material. Both formulations have their advocates, and both can be derived from consistent theoretical frameworks. Experiments have been conducted over the years attempting to resolve the controversy, but different experiments seem to support different formulations depending on exactly what is being measured. The issue is not merely a matter of definition but touches on fundamental questions about how energy and momentum are distributed between light and matter, about what we mean by the momentum of a photon in a medium, and about how to properly account for the momentum carried by the material itself when light passes through it. Recent work has suggested that both formulations may be correct in different contexts, that they represent different ways of partitioning momentum between the light field and the material, and that careful attention to what is actually being measured in experiments can reconcile the apparent contradiction. But the Abraham-Minkowski controversy remains a fascinating example of how even in classical physics, even in situations we encounter in everyday optical experiments, there can be deep conceptual puzzles about the correct way to describe what is happening. It reminds us that understanding is layered, that we can use theories successfully without fully grasping all their implications, and that nature always holds surprises for those who look closely enough. As we turn our attention from the cosmic scale to the world beneath our feet and the materials that surround us, we might expect firmer ground, more complete understanding. After all, we live on Earth's surface. We manipulate matter in laboratories. We have studied the substances and processes of our planet for centuries. Yet here too we find mysteries that resist solution. Phenomena that work in nature but defy our attempts to fully explain or reproduce them, and systems so complex that our best mathematical tools falter before them. The Earth itself harbors secrets in its depths, and the materials we use every day sometimes behave in ways we cannot quite account for. These mysteries may seem more mundane than questions about the origin of the universe or the nature of black holes, but they are no less profound, and in some ways they are more humbling precisely because they concern things we can touch and measure directly. Consider the phenomenon of superconductivity, the ability of certain materials to conduct electricity with absolutely zero resistance. When a material becomes superconducting, electric current can flow through it forever without losing energy, without generating heat, without any of the friction that normally accompanies the movement of electrons through matter. This remarkable property was first discovered in 1911 when mercury was cooled to just a few degrees above absolute zero. For decades, superconductivity remained a phenomenon confined to extremely low temperatures, requiring expensive and cumbersome cooling systems using liquid helium. Then, in 1986, a breakthrough occurred. Researchers discovered ceramic materials that became superconducting at much higher temperatures, above the boiling point of liquid nitrogen. These high-temperature superconductors revolutionized the field and opened new possibilities for practical applications. But they also introduced a profound mystery that persists to this day. We understand conventional low-temperature superconductivity quite well through a theory called BCS theory, which describes how electrons pair up and move through the material in a coordinated quantum state. But high-temperature superconductors do not fit this framework. The mechanism by which they achieve zero resistance at temperatures that should be far too hot for BCS theory to work remains unknown. The materials are complex, often involving copper oxide layers with intricate crystal structures, and their behavior suggests that strong quantum correlations and exotic phases of matter are at play. Numerous theories have been proposed, invoking everything from magnetic fluctuations to unusual pairing mechanisms to entirely new states of quantum matter. Yet despite intense research effort spanning nearly 4 decades, we still lack a complete, accepted explanation for how high-temperature superconductivity works. We can manufacture these materials and use them in applications like powerful magnets and sensitive detectors, but we cannot fully explain why they work. It is as though we have discovered a new technology by accident and are now trying to reverse engineer the principles that make it possible. The challenge of understanding complex systems appears again in one of physics' oldest unsolved problems: turbulence. When fluids flow smoothly at low speeds, their motion is orderly and predictable, characterized by parallel layers sliding past one another. But increase the speed or disturb the flow, and something dramatic happens. The fluid breaks into chaotic eddies and swirls, structures within structures, motion that appears random yet is governed by deterministic equations. This is turbulence, and it surrounds us constantly. It is present in the air flowing over an airplane wing, in the blood flowing through our arteries, in rivers and ocean currents, in the roiling gases of stars, in the plasma that fills much of the universe. The equations that describe fluid motion, the Navier-Stokes equations, have been known for nearly 2 centuries. We can write them down easily enough, But solving them for turbulent flows is another matter entirely. Turbulence involves motion across an enormous range of scales simultaneously, from large swirls down to the smallest eddies where energy is finally dissipated as heat. These scales interact in complex, non-linear ways that make analytical solutions essentially impossible for realistic situations. Even numerical simulations struggle because accurately representing turbulent flow requires resolving all these scales, demanding computational resources that quickly become prohibitive. Weather prediction is fundamentally limited by turbulence. The atmosphere is a turbulent fluid, and tiny uncertainties in initial conditions grow exponentially, setting a hard limit on how far into the future we can accurately forecast weather. Ocean circulation, which plays a crucial role in climate, is driven by turbulent processes that we cannot fully model. The formation of stars and planets involves turbulent flows of gas and dust. Understanding turbulence better would improve our ability to predict and control countless phenomena, yet the problem has resisted full solution. We have some statistical theories that describe certain aspects of turbulence. We have empirical rules and approximations that work in specific situations, but we lack a complete theory. The Clay Mathematics Institute has offered $1 million prize for proving whether smooth solutions to the Navier-Stokes equations always exist or whether they can develop singularities, infinite values in finite time. This mathematical question goes to the heart of whether turbulence is fully contained within our current framework or whether it represents something fundamentally beyond our equations. The solid Earth beneath us holds mysteries as well. Geological processes that shape the planet but resist complete explanation. One such puzzle concerns the formation of large granite bodies, the vast plutons that form the cores of mountain ranges. Granite is an intrusive igneous rock, meaning it crystallizes from magma that cooled underground rather than erupting at the surface. Some granite bodies are enormous, extending for hundreds of kilometers and representing millions of cubic kilometers of crystallized magma. But how did space open up in Earth's crust to accommodate these vast volumes of molten rock? When magma rises through the crust, it must displace or deform the rock around it. For small intrusions, this is not difficult to understand. The magma can wedge open fractures, push aside surrounding rock, or melt its way through. But for truly enormous magma chambers, the problem becomes severe. The surrounding rock has to go somewhere. Various mechanisms have been proposed. Perhaps the magma melts and assimilates large amounts of surrounding rock, incorporating it into the magma itself, though this process has limits and would change the magma's composition in ways not always observed. Perhaps the roof rock is lifted up, deforming the surface above, though many plutons show no evidence of such large-scale uplift. Perhaps blocks of roof rock founder and sink into the magma, making space from above. Perhaps extension of the crust creates space through stretching and thinning. Likely, multiple mechanisms operate together in different proportions depending on the specific geological setting. But detailed studies of large plutons often reveal features that are difficult to reconcile with any single mechanism or combination of mechanisms. The space problem in Pluton emplacement remains an active area of research, with geologists examining the structural relationships, the timing of deformation, and the thermal history of these bodies to piece together how they formed. It is a reminder that even processes occurring in the Earth's crust, at depths of only a few kilometers, can be difficult to fully reconstruct and understand. Even more mysterious and potentially more dangerous are supervolcanoes, volcanic systems capable of eruptions far larger than anything witnessed in recorded human history. A supervolcano eruption can eject hundreds or even thousands of cubic kilometers of material, creating a caldera tens of kilometers across and affecting global climate for years. There have been such eruptions in the past, and there will be more in the future. Yellowstone in the United States, Toba in Indonesia, Taupo in New Zealand. These are all supervolcano systems with histories of massive eruptions. But predicting when the next eruption might occur is extraordinarily difficult, bordering on impossible with current knowledge. Unlike typical volcanoes, which form prominent mountains and show frequent activity, supervolcano systems are often hidden. The magma chamber lies deep underground, perhaps 10 to 15 kilometers down, with no obvious surface expression except hot springs, geysers, and subtle ground deformation. The magma accumulates over hundreds of thousands of years, slowly melting and pooling until some threshold is reached. But what exactly that threshold is, and how to recognize when it is being approached, remains unclear. We can monitor these systems with seismometers that detect earthquakes caused by magma movement, with GPS stations that measure ground deformation as the magma chamber inflates or deflates, with gas sensors that analyze volcanic emissions for chemical changes. Yet these tools give us only indirect glimpses of what is happening kilometers below. The magma chamber is opaque to our instruments, its size and state of crystallization uncertain. Small earthquakes and ground uplift could indicate that eruption is imminent, or they could be normal fluctuations in a system that will remain dormant for millennia. The timescales are so long and the events so rare that we have essentially no historical record to calibrate our understanding. The last supervolcano eruption was Taupo approximately 1800 years ago, and before that Toba around 74,000 years ago. With such sparse data, building predictive models is extremely challenging. We can say that these systems are capable of catastrophic eruptions, but we cannot say with confidence when they might occur, giving us a sobering example of a natural hazard we can identify but not yet predict. Deeper still, the Earth's mantle presents fundamental puzzles about how heat moves through the interior of our planet. The mantle is the thick layer of hot, solid rock between the crust and the core, extending nearly 3,000 kilometers down. Though solid, the mantle flows very slowly over geological time, driven by convection as hot material rises and cool material sinks. This convection is ultimately responsible for plate tectonics, volcanism, and the recycling of Earth's crust. But the details of mantle convection remain poorly understood. The mantle is not uniform. It contains compositional variations, differences in temperature, and regions with different mechanical properties. How these variations affect the pattern of convection is difficult to determine. Laboratory experiments can study the behavior of mantle minerals under high pressure and temperature, but replicating mantle conditions over the entire pressure and temperature range is challenging, and scaling small laboratory experiments to planetary dimensions involves considerable uncertainty. Seismology gives us snapshots of the mantle structure by measuring how earthquake waves travel through it, revealing faster and slower regions that correspond to cooler and hotter rock. But converting these seismic images into detailed maps of temperature, composition, and flow remains an inverse problem fraught with ambiguity. Computer simulations attempt to model mantle convection, but they must make assumptions about the material properties, the initial conditions, and the boundary conditions, and different assumptions can lead to different convective patterns. The rheology of mantle rock, how it deforms under stress, depends on temperature, pressure, composition, grain size, water content, and other factors in complex ways that are not fully characterized. All of this uncertainty feeds into our limited understanding of how the mantle actually convects and how that convection has evolved over Earth's history. At a depth of approximately 660 kilometers, seismic waves reveal a sharp boundary where their velocity increases suddenly. This 660-kilometer discontinuity marks a major transition within the mantle, separating the upper mantle from the lower mantle. We know it exists because the seismic signature is clear and consistent worldwide. The cause is generally attributed to a phase transition in mantle minerals, where the crystal structure of certain minerals changes to a denser form at this depth due to the immense pressure. Specifically, the mineral ringwoodite is thought to break down into perovskite and ferropericlase. But while this explanation is widely accepted, the details remain debated. The exact mineralogy of the mantle at this depth is uncertain because we cannot directly sample it. The sharpness of the discontinuity, the way it varies from place to place, and how it interacts with mantle convection are all subjects of ongoing research. Some regions show a very sharp transition, while others show a more gradual change or even multiple smaller steps. These variations suggest that local temperature, composition, or other factors influence the phase transition in ways that are not fully understood. The 660-kilometer discontinuity may also act as a barrier to convection in some regions, with slabs of subducted oceanic crust piling up at this depth before eventually breaking through into the lower mantle, or it may be transparent to flow in other regions. The implications for how heat and material are transported through the mantle are significant, and uncertainties about this boundary translate into uncertainties about the dynamics of the entire planet. When we step back and consider Earth's thermal history over billions of years, we confront another puzzle: the planet's long-term heat balance. Earth radiates heat into space from its surface, heat that comes partly from the decay of radioactive elements in the crust and mantle, and partly from the primordial heat left over from the planet's formation. The balance between heat production and heat loss determines how the planet cools over time, which in turn affects the vigor of mantle convection, the thickness of the crust, the occurrence of volcanism, and the operation of the geodynamo in the core that generates Earth's magnetic field. But when we look back to the early history of the solar system, we find an apparent contradiction. The young Sun, based on stellar evolution models, should have been about 30% less luminous than it is today. With such a faint Sun, Earth should have been frozen, its surface temperature well below the freezing point of water. Yet geological evidence clearly indicates that liquid water existed on Earth's surface as far back as we can see in the rock record, nearly 4 billion years ago. This is the faint young sun paradox, and it suggests that Earth's early atmosphere must have had much stronger greenhouse warming than today, perhaps with higher concentrations of carbon dioxide, methane, or other greenhouse gases. But the details of how this worked, how the atmosphere maintained such high greenhouse gas levels, and how it transitioned to lower levels over time without freezing or boiling the planet, remain incompletely understood. The carbon cycle, weathering processes, the evolution of life, and volcanic outgassing all play roles, but constructing a complete self-consistent model that explains Earth's climate history from the early Archean eon to the present is an ongoing challenge. The problem touches on geology, atmospheric science, solar physics, and planetary science, requiring integration of knowledge from multiple fields. The motion of Earth's poles adds another layer of complexity to understanding our planet's dynamics. The geographic poles, the points where Earth's rotation axis intersects the surface, are not fixed. They wander slowly over time, a phenomenon called polar drift. Part of this drift is caused by changes in the distribution of mass within and on the planet. When ice sheets grow or shrink, when water moves between oceans and continents, when magma moves within the mantle, the planet's moment of inertia changes slightly, and the rotation axis adjusts. This is called true polar wander. There is also the separate phenomenon of the magnetic poles wandering, which results from changes in the flow of liquid iron in Earth's outer core. Disentangling these effects and understanding their causes requires careful analysis of geological, geophysical, and paleomagnetic data. The mechanisms driving polar drift involve the interplay of climate processes, the ice sheets responding to orbital variations and greenhouse gas changes, isostatic adjustment as land rises or sinks in response to changing ice loads, and deep Earth processes related to mantle convection and core dynamics. Each of these processes operates on different timescales and affects the others in complex feedback loops. For example, ice sheet growth changes sea level and land distribution, which affects climate, which affects ice sheets. Mantle convection influences the geoid, the shape of Earth's gravitational field, which affects ocean circulation and potentially climate. Separating these interwoven influences to understand what drives polar drift at any given time is difficult. The problem is not that we lack theories, but that we have too many contributing factors and insufficient data to uniquely determine their relative importance. Sometimes the most perplexing mysteries involve substances that are common in nature yet defy our attempts to recreate them in the laboratory. Dolomite is a mineral, a carbonate of calcium and magnesium, that forms enormous rock formations around the world. Ancient dolomite deposits are abundant, indicating that it formed readily throughout Earth's history. Yet when geochemists try to precipitate dolomite in the laboratory under conditions that should mimic natural environments, they largely fail. At room temperature and normal surface conditions, dolomite simply will not form in experiments, or forms only in trace amounts over very long times. This is the dolomite problem, a puzzle that has vexed geologists for decades. We know dolomite exists. We can analyze its crystal structure, we understand its composition, but we cannot easily make it. The problem seems to be kinetic. Thermodynamically, dolomite should be the stable phase under many conditions, but there is a high activation energy barrier that prevents calcium and magnesium from arranging themselves into the proper crystal structure. In nature, various factors might help overcome this barrier. Perhaps the presence of certain microorganisms that alter the local chemical environment plays a role, as some studies have suggested. Perhaps elevated temperatures, even slightly above normal surface conditions, are necessary, or perhaps very long timescales allow the slow nucleation and growth of dolomite crystals. Perhaps specific chemical conditions involving sulfate or other dissolved ions are required. Many ideas have been tested, and some conditions have been found that encourage dolomite formation, but a complete understanding that explains why dolomite is so abundant in ancient rocks yet so reluctant to form in experiments remains elusive. The dolomite problem is a humbling reminder that even for common minerals, even for substances we can hold in our hands and study in detail, the processes of formation can be subtle and difficult to replicate. Another geological enigma involves banded iron formations, distinctive rock layers that consist of alternating bands of iron-rich minerals and silica. These formations are found primarily in rocks older than about 1.8 billion years and represent the deposition of enormous quantities of dissolved iron that was carried in the ancient oceans. The standard explanation for banded iron formations invokes the rise of oxygen in Earth's atmosphere. Early Earth had an oxygen-poor atmosphere, and iron dissolved readily in seawater. Then, As photosynthetic organisms evolved and began producing oxygen, the oxygen reacted with the dissolved iron, causing it to precipitate out of the water and settle to the seafloor. The banded structure is thought to reflect periodic variations in oxygen production or iron supply, perhaps related to seasonal cycles, volcanic activity, or other oscillating processes. But this explanation, while broadly accepted, leaves many details unresolved. Why did the banding occur at such regular intervals? Why did banded iron formation deposition largely cease after a certain point in Earth's history, even though iron continued to enter the oceans? Why are some banded iron formations so thick and extensive, representing such enormous volumes of precipitated iron? The transition from an iron-rich ocean to an iron-poor ocean as oxygen levels rose should have been a complex process involving ocean circulation, the spatial distribution of oxygen-producing organisms, the chemistry of seawater, and the nature of seafloor sediments. Some researchers have proposed alternative or additional mechanisms, such as the role of hydrothermal vents in supplying iron, or the possibility that different types of microorganisms played a role in oxidizing and precipitating iron. The full story of banded iron formations remains a subject of active research, with implications for understanding the evolution of Earth's atmosphere, the early biosphere, and the cycling of elements in the ancient oceans. It is another example of how Earth's past holds secrets written in rock, secrets we can read partially but not yet completely. When we think of unexplored frontiers, our minds often turn skyward to distant planets and galaxies. Yet the vast majority of our own planet remains a mystery, hidden beneath the waves that cover more than 70% of Earth's surface. The ocean depths are as alien and inaccessible as outer space in many ways, and our knowledge of what lies below is fragmentary at best. We have mapped the surface of Mars in greater detail than we have mapped our own ocean floor. We have sent probes to the outer reaches of the solar system while leaving the abyssal plains and deep trenches of our home planet largely unvisited. The ocean conceals entire ecosystems, geological features, and processes that we have only begun to glimpse, and with each new expedition into the deep, we find that our ignorance is vaster than we imagined. Current estimates suggest that we have thoroughly mapped less than 25% of the ocean floor at high resolution. This statistic is somewhat misleading because we have coarse data covering the entire seafloor derived from satellite measurements of the ocean surface, which reveal the shape of the seafloor through subtle variations in sea level caused by underwater topography. But this satellite data has relatively low resolution, measured in kilometers. High-resolution mapping requires ships equipped with multi-beam sonar systems to cruise back and forth, scanning the seafloor in detail. This is time-consuming and expensive, and with hundreds of millions of square kilometers of ocean floor to cover, the task is monumental. The regions we have mapped in detail are often those near coastlines, along shipping routes, or in areas of specific scientific or commercial interest. Vast stretches of the deep ocean remain known only through those coarse satellite-derived maps. This means we lack detailed knowledge of underwater mountains, canyons, hydrothermal vent fields, and other features that could harbor unique ecosystems or geological processes. Entire mountain ranges lie hidden beneath the waves, their peaks never seen by human eyes or instruments. The seafloor is not a featureless plain but a landscape as varied and complex as any continent, with its own mountains and valleys, volcanoes and faults, and we have barely begun to chart it. Among the most extreme and least accessible places on Earth is the Mariana Trench in the western Pacific Ocean, the deepest oceanic trench on the planet. At its deepest point, the Challenger Deep, the seafloor lies nearly 11 kilometers below the surface, deeper than Mount Everest is tall. The pressure at this depth is crushing, more than 1,000 times atmospheric pressure at sea level, enough to instantly collapse most human-made structures. Only a handful of crude submersibles have ever descended to the bottom of the Challenger Deep, and only a few robotic vehicles. The environment is utterly dark, cold, and seemingly inhospitable, yet life exists even here. Each expedition to the Hadal Zone, the name given to ocean depths below 6 kilometers, has revealed surprising biodiversity. Amphipods the size of a human hand, snailfish with translucent bodies, microorganisms thriving in the sediment, all adapted to pressures and conditions that would be instantly lethal to organisms from the surface. But our visits to these depths have been brief and widely spaced. We know almost nothing about the ecology of the Hadal Zone, how energy flows through these ecosystems, how species are distributed across different trenches, or how they have evolved to tolerate such extremes. The technology required to explore the deepest ocean is sophisticated and rare. Submersibles must withstand immense pressure, carry life support systems, and navigate in complete darkness. Each dive is a major undertaking, and the total amount of time humans have spent at full Hadal depths can be measured in hours. We have spent far more time on the surface of the Moon than we have at the bottom of Earth's deepest trenches. Even shallower depths, though more accessible than the Hadal Zone, remain largely unknown. The ocean's twilight zone, also called the mesopelagic zone, extends from about 200 meters to 1,000 meters depth. Here, sunlight fades to a dim blue glow and then disappears entirely, and the water is cold and under significant pressure. This zone is difficult to study because it is too deep for conventional diving and too shallow to be a primary target for deep-sea submersibles, falling into a kind of exploratory gap. Yet recent research suggests that the twilight zone may contain more fish biomass than all the shallow waters of the ocean combined. Vast schools of small fish and other organisms migrate vertically each day, rising toward the surface at night to feed and descending into the twilight zone during daylight to avoid predators. This daily migration may be the largest movement of animals on the planet in terms of biomass. But we have only begun to quantify it. Traditional net sampling gives us snapshots, but netting small, fragile organisms at depth often damages them, making identification difficult and providing limited information about behavior. Acoustic surveys can detect schools of fish but cannot always distinguish species. Cameras and remotely operated vehicles give visual impressions but cover only tiny areas. The true extent of life in the twilight zone, the number of species, their interactions, and their role in the ocean's food web and carbon cycle remain largely unknown. This matters because these organisms play a crucial role in the biological pump, the process by which carbon is transported from the surface ocean to the deep sea, affecting global carbon cycles and climate. Underestimating the biomass in the twilight zone means underestimating a major component of the ocean ecosystem and its influence on the planet. The ocean also produces sounds that we cannot always explain. For decades, hydrophones placed in the ocean for various purposes, including monitoring for submarine activity during the Cold War, have recorded strange and powerful sounds emanating from the deep. Some of these sounds have been identified. The bloop, an ultra-low frequency sound detected in 1997, was eventually attributed to ice calving from Antarctic glacier. The upsweep, a persistent sound that has been detected since 1991, is thought to originate from volcanic or hydrothermal activity in the Pacific. But other sounds remain mysterious. Unexplained clicks, hums, and groans appear in recordings, sometimes as isolated events and sometimes as recurring patterns. The ocean is noisy, filled with the sounds of waves, marine life, geological activity, and human-made noise from ships and industry. Disentangling these sources and identifying anomalous sounds is challenging. Marine mammals, particularly whales, produce complex vocalizations that can travel hundreds of kilometers through the water, and some species may produce sounds we have not yet catalogued. Geological processes, including underwater landslides, volcanic eruptions, and the grinding of tectonic plates, generate powerful low-frequency sounds. But occasionally, a sound is recorded that does not fit known sources, too loud or too strange to be easily explained, and lacking any obvious origin. These acoustic mysteries remind us that the ocean is not just visually hidden but acoustically opaque, a realm where sound is the primary means of long-distance communication and sensing, and where we are still learning to interpret what we hear. The mysteries of Earth are not confined to the ocean. The land holds its own enigmas, phenomena observed repeatedly yet poorly understood. In forests around the world, circular clearings sometimes appear, areas where trees are stunted or absent, forming nearly perfect rings tens of meters across. These forest rings, also called fairy rings when they occur in grassy areas, have been noted for centuries and attributed to everything from fungal activity to dancing fairies in folklore. In some cases, the rings are indeed caused by fungi. Certain mushroom species grow outward from a central point in a circular pattern, and the fungal mycelia in the soil can affect plant growth, either enhancing it through symbiotic relationships or inhibiting it through competition for nutrients or the release of toxic compounds. But not all forest rings have clear fungal associations. Some appear in regions with no obvious fungal explanation, and their causes remain speculative. Soil composition variations, localized disease, differences in hydrology, historical land use, even subtle topographic effects have all been proposed. In some cases, multiple factors may interact to create the ring structure. But a comprehensive explanation that accounts for all observed forest rings across different environments and ecosystems remains elusive. They are a reminder that even familiar landscapes hold patterns we do not fully understand, that the natural world produces structures and forms through processes we have not completely deciphered. Even more perplexing are reports of a substance called star jelly, gelatinous masses that occasionally appear on the ground, often after rainstorms or meteor showers. Descriptions vary, but typically star jelly is described as a translucent or whitish jello-like substance, sometimes with a foul odor, that evaporates or decomposes quickly, leaving little trace. Historical accounts of star jelly go back centuries, with various folkloric explanations linking it to falling stars or atmospheric phenomena. Modern attempts to analyze samples have yielded inconclusive results, partly because the material degrades so rapidly. Some samples have been identified as the remains of frogs or toads regurgitated by predators, with the bones and organs removed, leaving only the gelatinous oviducts. Other samples appear to be colonies of cyanobacteria or other microorganisms that form gelatinous sheaths. Some may be slime molds in certain stages of their life cycle. But not all reported instances of star jelly have been satisfactorily explained, and the ephemeral nature of the substance makes systematic study difficult. It occupies a strange space between genuine natural phenomenon and misidentified biological material, with enough reports and enough variation that a single explanation seems inadequate. The mystery of star jelly endures partly because of this ambiguity, because the evidence disappears before it can be properly examined, leaving only anecdotal accounts and speculation. Another elusive phenomenon is ball lightning, a rare and poorly understood form of atmospheric electricity. Unlike ordinary lightning, which appears as a brilliant branching flash lasting a fraction of a second, ball lightning is reported to manifest as a glowing sphere, typically the size of a grapefruit but sometimes much larger, that floats or moves through the air, often inside buildings or aircraft. It persists for several seconds or even minutes before disappearing, sometimes with a loud pop or hiss, sometimes silently. Witnesses describe it passing through windows or walls without causing damage, moving erratically, and exhibiting a range of colors. The phenomenon is unpredictable, appearing most commonly during thunderstorms but sometimes in calm weather. Because it is so rare and so brief, ball lightning has been extremely difficult to study scientifically. Most of what we know comes from eyewitness accounts, which are inherently subjective and often come from people who were startled or frightened by the experience. Very few photographs or videos of ball lightning exist, and those that do exist are often of poor quality or disputed authenticity. Laboratory attempts to recreate ball lightning have had limited success. Researchers have produced glowing plasma spheres using high-voltage discharges, microwave radiation, and other techniques, and some of these laboratory phenomena share characteristics with reported ball lightning. But whether these experiments truly replicate natural ball lightning remains uncertain. Various theories have been proposed for what ball lightning might be. It could be a plasma held together by electromagnetic fields, perhaps related to the electromagnetic pulse generated by a lightning strike. It could involve vaporized silicon from soil, which forms luminous silicon nanoparticles when oxidized. It could be a kind of chemical reaction involving atmospheric gases. Or it could be something else entirely, a phenomenon that requires new physics to explain. The rarity and unpredictability of ball lightning make it a frustrating subject for scientific investigation, one of those phenomena that seems to exist on the boundary between observation and myth, real enough that thousands of people have reported it, yet elusive enough that we cannot study it systematically. When we look beyond Earth to our neighboring planets, we find cautionary tales about how planetary environments can evolve in unexpected and catastrophic ways. Venus, similar to Earth in size and mass, orbits slightly closer to the Sun. In its distant past, Venus may have had oceans and a climate not entirely dissimilar from early Earth. But something went catastrophically wrong. Today, Venus is a hellscape, with surface temperatures hot enough to melt lead, atmospheric pressure 90 times that of Earth's surface, and clouds of sulfuric acid. The entire planet is covered by a thick atmosphere of carbon dioxide that traps heat through an extreme greenhouse effect. What caused Venus to transform from a potentially habitable world into this inferno? The leading theory involves a runaway greenhouse effect. As Venus received slightly more solar energy than Earth due to its closer orbit, more water evaporated into the atmosphere. Water vapor is a powerful greenhouse gas, so this caused further warming, which led to more evaporation in a feedback loop. Eventually, the oceans boiled away entirely, and the water vapor in the upper atmosphere was broken apart by ultraviolet light, with the hydrogen escaping to space and the oxygen reacting with rocks or escaping as well. Without water to help sequester carbon dioxide through weathering and the carbonate silicate cycle, carbon dioxide accumulated in the atmosphere, mostly from volcanic outgassing. The greenhouse effect intensified until the planet reached its current state. But the details of this process are uncertain. When did it happen? How quickly? Could it have been avoided if Venus had been just slightly farther from the Sun, or if its rotation had been different, or if some other factor had been altered. And most troubling for us, could a similar runaway greenhouse effect happen on Earth? The differences between Earth and Venus, the factors that kept Earth habitable while Venus became uninhabitable, are not entirely clear. Venus serves as a stark reminder that planetary climates can have tipping points, thresholds beyond which feedback loops drive systems into new and potentially irreversible states. Understanding what happened to Venus is not just a matter of planetary science curiosity, but has implications for understanding climate stability on Earth and the limits of habitability. Even the origin of Earth's water, the substance that covers most of our planet's surface and is essential for life, remains a subject of debate. The early Earth formed through the accretion of material in the inner solar system, a region that was hot and where volatile substances like water should have been scarce. Rocky planets like Earth were expected to be dry. Yet clearly Earth has abundant water. Where did it come from? One possibility is that water was delivered by comets, icy bodies from the outer solar system that occasionally impact the inner planets. Comets contain large amounts of water ice, and a barrage of comet impacts in Earth's early history could have delivered the oceans. However, when scientists analyze the isotopic composition of water in comets, specifically the ratio of deuterium to hydrogen, they often find it does not match Earth's ocean water very well. The deuterium to hydrogen ratio in many comets is higher than in Earth's water, suggesting that comets alone cannot account for all of Earth's water. Another possibility is that water was delivered by asteroids, particularly a class of asteroids called carbonaceous chondrites, which contain hydrated minerals. These asteroids formed farther from the Sun than Earth did, but not as far out as comets, and their water isotope ratios are a better match for Earth's oceans. Yet the dynamics of how enough water-bearing asteroids could have reached Earth in the right quantities and at the right times are complex. Perhaps Earth's water came from a combination of sources, some from the nebula gas that was incorporated into minerals during the planet's formation, some from asteroids, and perhaps a smaller contribution from comets. Disentangling these contributions requires analyzing isotope ratios not just of hydrogen but also of other elements like nitrogen and noble gases, and comparing them across different solar system bodies. The picture that emerges is complicated, with different lines of evidence sometimes pointing in different directions. The origin of Earth's water remains an active research area, with implications for understanding how planets acquire volatile elements and how common water might be on rocky planets elsewhere in the universe. If water delivery to Earth required a specific set of circumstances, a particular configuration of the early solar system or a fortuitous timing of impacts, then Earth-like water-rich worlds might be rare. If water delivery is a natural outcome of planet formation in a wide range of systems, then water worlds might be common. The answer affects our assessment of the likelihood of life elsewhere and our understanding of what makes a planet habitable. These mysteries, whether hidden in ocean depths, scattered across forest floors, flickering in storm-tossed skies, or written in the geological and atmospheric histories of planets, share a common thread. They occupy the spaces where our knowledge is incomplete, where observation outpaces explanation, where the complexity of natural systems defies easy categorization. They are humbling in their persistence, reminding us that the universe, even the small corner of it we call home, is far richer and stranger than our theories yet encompass. Each mystery invites inquiry, and each attempt to solve them expands our understanding even when it does not provide final answers. In this way, the unknown is not an obstacle but an invitation, a call to look more closely, to ask better questions, and to remain open to the possibility that nature has surprises we have not yet imagined. As we turn our attention to the living world, we encounter mysteries that strike at the very heart of existence itself. Life, in all its staggering complexity and diversity, raises questions that span from its deepest origins to the limits of its duration, from the simplest chemical reactions to the emergence of intelligence in unexpected places. The boundary between living and non-living, the mechanisms by which simple organisms become complex, the nature of aging and death, these are not merely academic puzzles but fundamental questions about what it means to be alive and how life persists in a universe governed by entropy and decay. Perhaps no question in biology is more profound or more vexing than the origin of life itself. How did the first living cell arise from non-living chemistry? We know that life on Earth began at least 3.5 billion years ago, possibly earlier, emerging in the primordial oceans when the planet was still young and violent. But the transition from simple organic molecules to a self-replicating, metabolizing, evolving system seems almost miraculous when we examine it closely. A living cell, even the simplest bacterial cell, is breathtakingly complex. It contains thousands of different proteins, each folded into a precise three-dimensional shape and performing specific functions. It has a genome, a sequence of DNA or RNA that encodes information and can be copied and passed on. It has a membrane that separates the cell's interior from the external environment while allowing selective exchange of materials. It has metabolic pathways, intricate sequences of chemical reactions that extract energy from the environment and build the molecules the cell needs. All of these components must work together in coordinated fashion for the cell to live. The statistical improbability of all these pieces assembling spontaneously by chance seems overwhelming. If you were to randomly combine amino acids, the building blocks of proteins, the odds of forming even a single functional protein of modest size are astronomically small. And a cell needs not just one protein but thousands of them, all working in concert. How could such a system arise without guidance, without foresight, through nothing but chemistry and probability? Various theories attempt to explain this. The RNA world hypothesis suggests that early life was based on RNA rather than DNA, because RNA can both store genetic information and catalyze chemical reactions, potentially serving as both genome and enzyme. Perhaps the first replicating molecules were simple RNA strands that gradually became more complex. The metabolism first hypothesis proposes that self-sustaining networks of chemical reactions arose first, with genetic molecules coming later. Perhaps life began in hydrothermal vents on the ocean floor, where chemical energy from the Earth's interior drove reactions that built organic molecules. Perhaps life began in shallow tidal pools where cycles of wetting and drying concentrated molecules and promoted complex chemistry. Each scenario has its advocates and its problems. Laboratory experiments have shown that some of the necessary chemical steps can occur under plausible early Earth conditions, but bridging the gap from simple organic chemistry to a living, replicating cell remains an unsolved challenge. The origin of life is not just improbable but seems to require a sequence of unlikely events occurring in the right order, and we do not yet understand how nature achieved this feat. Once life did emerge, it remained relatively simple for billions of years. Bacteria and archaea, single-celled organisms without nuclei, dominated the planet for most of Earth's history. Then, around 540 million years ago, something extraordinary happened. In a geological blink of an eye, a period of perhaps 10 to 20 million years, an explosion of diversity occurred. This event, known as the Cambrian explosion, saw the emergence of most of the major animal body plans, the fundamental architectures that define the different phyla of the animal kingdom. Before the Cambrian, animal life was mostly simple, soft-bodied, and difficult to categorize. After the Cambrian, we find fossils of creatures with hard shells, jointed appendages, complex eyes, segmented bodies, and all the diversity of forms that characterize modern animals. Trilobites scuttled across the seafloor, predators with grasping appendages hunted prey, organisms with calcium carbonate shells appeared in abundance. The suddenness of this diversification is startling and demands explanation. What triggered the Cambrian explosion? Various hypotheses have been proposed. Perhaps a rise in atmospheric oxygen reached a threshold that allowed larger, more active animals to evolve. Perhaps the evolution of predation created an evolutionary arms race, with prey developing shells and armor and predators developing better ways to capture and consume them. Perhaps the evolution of eyes allowed animals to sense their environment in new ways, opening up ecological niches and driving diversification. Perhaps changes in ocean chemistry made it easier for animals to build mineralized skeletons. Perhaps genetic innovations, such as the evolution of Hox genes that control body plan development, provided the toolkit for building complex body forms. Likely, multiple factors work together, but pinpointing the exact sequence of causes and effects remains elusive. The fossil record from the Cambrian is rich but still incomplete, and many of the soft-bodied animals that must have existed left no trace. The Cambrian explosion raises fundamental questions about how evolution works, whether diversification tends to occur in bursts when new ecological or genetic opportunities arise, and what limits or enables the generation of biological novelty. Among the many innovations that appeared in the history of life, one of the most visually striking is bioluminescence, the ability of living organisms to produce light through chemical reactions. Bioluminescence has evolved independently many times in different lineages, appearing in bacteria, fungi, jellyfish, fish, insects, and other groups. In the deep ocean, where sunlight never penetrates, bioluminescence is common, used for attracting prey, communicating with mates, confusing predators, or illuminating the darkness. Yet the evolutionary origin of bioluminescence in animals is mysterious. The biochemical pathways that produce light are complex, involving specialized proteins called luciferins and enzymes called luciferases that catalyze light-producing reactions. These systems do not appear to have clear precursors in non-luminescent organisms. Bioluminescence seems to have appeared suddenly in the fossil record without obvious intermediate stages, though of course the light-producing chemistry itself does not fossilize, making this difficult to trace. What evolutionary pressures drove the development of bioluminescence? What were the first uses of biological light, and how did organisms stumble upon the chemistry needed to produce it? Some researchers suggest that the chemistry of bioluminescence may have originally evolved for purposes other than light production, perhaps as a way to neutralize toxic oxygen species or to facilitate certain metabolic reactions, and that the light-emitting property was initially a byproduct that later became co-opted for communication or other functions. But the details remain speculative, and the independent evolution of bioluminescence in so many different groups suggests that once the right conditions exist, life finds ways to generate light, though the paths to that innovation are not well understood. Even the nature and origin of viruses, among the simplest biological entities, remain matters of debate. Viruses occupy a strange position at the boundary of life. They consist of genetic material, either DNA or RNA, wrapped in a protein coat, and sometimes an outer envelope derived from host cell membranes. They cannot reproduce on their own and must infect living cells, hijacking the cell's machinery to make copies of themselves. Are viruses alive? They do not metabolize, they do not grow, they do not respond to stimuli in the way cells do. Yet they evolve, they adapt to their hosts, they carry genetic information and pass it on. The question of whether viruses are living or non-living is almost philosophical, hinging on how we define life. But beyond this question lies another: where did viruses come from? Three main hypotheses compete. The regressive hypothesis suggests that viruses are degenerate forms of cellular life, perhaps intracellular parasites that lost more and more of their cellular machinery over evolutionary time until only the bare essentials for replication remained. The escape hypothesis proposes that viruses originated from pieces of cellular genetic material, perhaps mobile genetic elements or plasmids, that gain the ability to move between cells by wrapping themselves in proteins. The virus-first hypothesis suggests that viruses are ancient, perhaps predating cellular life, representing a lineage that evolved separately and has always been dependent on cells for replication. Each hypothesis has some support and some difficulties. The diversity of viruses is enormous, with vast differences in genome size, structure, and replication strategy, and it is possible that different groups of viruses have different origins. The discovery of giant viruses in recent years, with genomes larger than some bacteria and carrying genes not found in typical viruses, has complicated the picture further. These giant viruses blur the line between virus and cell, possessing some metabolic genes and a complexity that challenges simple categorizations. The origin and nature of viruses remain open questions, with implications for understanding the early evolution of life and the diversity of biological strategies. Life as we know it depends on oxygen for energy production in most organisms. The mitochondria inside our cells burn oxygen to generate the ATP molecules that power cellular processes. Yet recently, a startling exception was discovered. Hennegia salmonicola, a tiny parasite that infects salmon, has lost the ability to respire aerobically. It has no mitochondrial genome, and it survives without oxygen, making it the only known animal that is truly anaerobic. This discovery overturned the assumption that all animals require oxygen at some level. How does Hennegia survive? It lives as a parasite inside fish tissue, an environment that is oxygen poor, and it apparently derives energy through fermentation or by scavenging molecules from its host. The loss of mitochondrial respiration is an extreme example of reductive evolution, where an organism loses complex features because they are no longer necessary or beneficial in its particular ecological niche. But it raises questions about the limits of animal physiology and the diversity of metabolic strategies. If one animal can abandon oxygen, might there be others? The discovery was made through genomic sequencing, which revealed the absence of a mitochondrial genome, something that had been thought essential for all animals. Hennegia reminds us that evolution can take unexpected paths, that organisms can shed capabilities we think are fundamental, and that the definition of what is necessary for animal life may be more flexible than we assumed. Intelligence, we typically assume, requires a brain or at least a nervous system. Yet some organisms challenge this assumption in remarkable ways. Slime molds are single-celled organisms that can grow to cover large areas, forming networks of tubes that transport nutrients. Despite having no brain, no neurons, no centralized information processing system, slime molds can solve complex problems. In laboratory experiments, Slime molds placed in mazes will find the shortest path between food sources. They can optimize network designs, recreating efficient transportation networks that resemble human-designed systems like railway maps. When researchers placed oat flakes, which slime molds like to eat, at positions corresponding to cities around Tokyo and placed a slime mold at Tokyo's location, the organism grew a network connecting the food sources that closely resembled the actual rail network around Tokyo, a design that engineers had spent years optimizing. How does a brainless organism do this? The slime mold operates through simple local rules. It extends tendrils in all directions, and those tendrils that find food are reinforced while those that find nothing retract. Nutrients flow through the network, and the tubes adjust their thickness based on flow efficiency. Through this process of growth, retraction, and reinforcement, the slime mold arrives at an optimized solution without any central planning or conscious thought. This is an example of distributed intelligence, where complex behavior emerges from simple interactions among components. The slime mold hints at forms of intelligence that do not rely on neural architecture, suggesting that information processing and problem-solving might be more widespread in nature than we think, and that our understanding of cognition may be too narrow, too focused on brains and nervous systems to encompass the full range of biological computation. The ocean is home to countless species of phytoplankton, microscopic photosynthetic organisms that drift in the sunlit surface waters. According to competitive exclusion principle, species that share the same resources and occupy the same ecological niche cannot coexist indefinitely. One species will inevitably outcompete the others, driving them to extinction or forcing them into different niches. Yet when we look at phytoplankton communities, we find dozens or even hundreds of species coexisting in the same body of water, all competing for the same basic resources: sunlight, carbon dioxide, and a limited set of nutrients like nitrogen and phosphorus. This is the paradox of the plankton, and it has puzzled ecologists for decades. How can so many species coexist when theory says they should not? Various explanations have been proposed. Perhaps the ocean environment is not as uniform as it appears, with small-scale variations in temperature, nutrient availability, and mixing creating a mosaic of microenvironments that allow different species to specialize. Perhaps disturbances, such as storms or grazing by zooplankton, prevent any one species from dominating by continually resetting the system. Perhaps the system is never at equilibrium, always changing, so that no species has time to completely exclude others. Perhaps there are trade-offs we do not fully understand, with different species being better adapted to different conditions that vary over time or space. Perhaps the competitive exclusion principle itself is too simplistic, not accounting for the complexity of real ecosystems where many factors interact. The paradox of the plankton remains an active area of research, with scientists using mathematical models, laboratory experiments, and field observations to try to understand how diversity is maintained in systems that seem too simple to support it. The answer likely involves a combination of factors, but fully resolving the paradox requires a deeper understanding of ecological dynamics than we currently possess. All living organisms age, accumulating damage and declining in function over time until eventually they die. Yet the mechanisms of aging remain surprisingly unclear. We know that cells and tissues degrade with age. DNA accumulates mutations and damage. Proteins misfold and aggregate. Telomeres, the protective caps on the ends of chromosomes, shorten with each cell division. Mitochondria become less efficient. Oxidative stress from reactive molecules damages cellular components. The immune system weakens. But which of these processes is the fundamental cause of aging, and which are merely consequences? Or is aging the result of many different processes acting together, with no single root cause? Some theories of aging focus on damage accumulation, the idea that aging results from the gradual buildup of molecular and cellular damage that the body cannot fully repair. Other theories emphasize programmed aging, suggesting that aging is a regulated process controlled by genes, perhaps a byproduct of developmental programs that continue to run after reproduction. Still, other theories propose that aging results from trade-offs, such as between reproduction and longevity, where organisms invest resources in reproduction at the expense of maintaining their bodies. The fact that different species age at vastly different rates, with some organisms like certain turtles and whales living for centuries while others like mice live only a few years, suggests that aging is not a fixed inevitable process but something that can be modulated by evolution. Yet we do not fully understand what determines lifespan, why some species have evolved long lives and others short, or whether there are fundamental biological limits to how long an organism can live. Research into aging has accelerated in recent years, with studies identifying specific genes and pathways that influence lifespan in model organisms, but translating these findings into a comprehensive theory of aging and potential interventions for humans remains a work in progress. Even something as familiar as blood types presents an evolutionary mystery. Humans have different blood types, most commonly categorized by the ABO system, where individuals can be type A, B, AB, or O depending on the presence or absence of certain antigens on the surface of red blood cells. These blood type differences are important for transfusions and can affect disease susceptibility, but why do different blood types exist at all? What evolutionary advantage, if any, do they confer? The ABO blood groups are ancient, shared with other primates, suggesting they have been maintained by evolution for millions of years. If one blood type were clearly superior, we might expect it to have swept through the population, but instead multiple types persist in roughly balanced proportions in most human populations. This suggests that there may be some form of balancing selection, where different blood types have advantages under different circumstances, preventing any one type from becoming universal. Some studies have found associations between blood type and susceptibility to certain diseases. For example, individuals with blood type O appear to have lower risk of severe malaria, while those with type A may have different risks for heart disease or certain infections. Perhaps in the past, when infectious diseases were major causes of death, having a diversity of blood types in a population provided resilience, ensuring that no single pathogen could wipe everyone out. But the evidence is not conclusive, and many of the observed associations are weak or inconsistent across populations. The persistence of blood type diversity may simply be neutral, maintained by genetic drift without strong selection in either direction. Or there may be subtle fitness effects that we have not yet detected. The mystery of blood types is a reminder that even well-studied aspects of human biology can lack clear evolutionary explanations. As medical science advances and life expectancy increases, questions about the ultimate limits of human lifespan become more pressing. How long can humans live? In recent centuries, average life expectancy has increased dramatically in developed countries, primarily due to reductions in infant mortality, control of infectious diseases, and improvements in nutrition and sanitation. But maximum lifespan, the age to which the oldest individuals live, has increased much more slowly. The oldest verified human lifespan is 122 years, achieved by Jean Calment of France. Despite many claims of people living longer, none have been conclusively verified. This has led some researchers to propose that there may be a biological limit to human lifespan, perhaps around 120 to 150 years, beyond which the accumulated damage and dysfunction of aging make continued life impossible. Studies analyzing demographic data have suggested that the rate of mortality increase with age may slow or plateau at very advanced ages, but the number of people reaching these extreme ages is so small that the statistics are uncertain. Other researchers argue that there is no fixed limit, that with sufficient medical intervention and understanding of aging processes, lifespan could be extended indefinitely. The question is not just academic but has implications for how we think about aging, healthcare, and the goals of medical research. If there is a hard biological ceiling on lifespan, then efforts to extend life may face diminishing returns beyond a certain point. If there is no such ceiling, or if it can be shifted through intervention, then radical life extension may be possible. The uncertainty reflects our incomplete understanding of what ultimately limits lifespan, whether it is the accumulation of specific types of damage that could in principle be repaired, or some more fundamental constraint built into the architecture of multicellular life. These mysteries of life, from its unlikely origins to its diverse forms and its inevitable end, weave through the fabric of biology, challenging our understanding at every scale. They remind us that living systems are not simple machines but intricate networks of processes, shaped by billions of years of evolution, constrained by physics and chemistry yet capable of astonishing complexity and adaptability. Each question we answer about life seems to reveal new questions waiting beneath. Each explanation we construct rests on assumptions that themselves require justification. And so we continue to probe, to experiment, to observe, driven by the fundamental desire to understand the phenomenon of which we ourselves are a part. The human body and mind, familiar as they are to us, harbor mysteries that touch on the most intimate aspects of our existence. We live inside these biological machines, navigate the world through them, experience consciousness within them, yet fundamental aspects of how they work remain puzzling. Some of these mysteries involve phenomena so common that we barely notice them, everyday experiences that occur without our conscious control. Others involve the deepest questions about how the brain creates mind, how physical matter gives rise to thought and memory and the sense of self. Between these extremes lies a landscape of partially understood processes, effects we can observe and measure but cannot fully explain. Consider the placebo effect, one of the most robust and perplexing phenomena in medicine. When people are given an inactive substance, a sugar pill or saline injection that contains no therapeutic ingredient, and are told it is a real medication, a significant percentage of them experience genuine improvement in their symptoms. This is not merely imagination or reporting bias. Measurable physiological changes occur. Pain decreases, as measured by both self-report and brain imaging showing reduced activity in pain processing regions. Parkinson's disease patients given placebo treatments show increased dopamine release in their brains. Depression lifts, inflammation markers change, even immune function can be affected. The placebo effect demonstrates that expectation and belief can trigger real biological responses, that the brain has the power to influence bodily systems in ways that mimic pharmaceutical intervention. But how does this work? What neural mechanisms translate expectation into physiological change? We know that areas of the prefrontal cortex involved in expectation and reward anticipation become active during placebo responses, and that these regions connect to systems controlling pain, emotion, and autonomic functions. But the detailed pathways, The specific molecular and cellular events that occur when a placebo produces healing remain incompletely mapped. Moreover, the placebo effect varies tremendously between individuals and conditions. Some people are highly responsive to placebos, others barely respond at all. Some medical conditions show strong placebo effects while others show minimal response. Understanding these variations and the underlying mechanisms could revolutionize how we think about healing and the relationship between mind and body, yet the placebo effect remains more observation than explanation. Even something as mundane as yawning defies complete understanding. We yawn when tired, when bored, when we see others yawn. Yawning occurs across species, observed in mammals, birds, reptiles, and fish. It appears early in human development, with fetuses yawning in the womb. Yet no single accepted explanation accounts for why we yawn. The traditional idea that yawning increases oxygen intake or removes carbon dioxide has been tested and found wanting. Studies show that breathing enriched oxygen or elevated carbon dioxide does not significantly affect yawning frequency. Other theories suggest yawning cools the brain, with the deep inhalation and stretching of the jaw increasing blood flow and helping regulate brain temperature. This might explain why yawning increases when ambient temperature is moderate, neither too cold nor too hot. But this theory does not fully account for contagious yawning, the phenomenon where seeing or hearing someone yawn triggers yawning in others. Contagious yawning appears linked to empathy and social bonding, more common in social species and between individuals with close relationships. Brain imaging shows that regions involved in self-awareness and social cognition activate during contagious yawning. Yet why evolution would link a physiological reflex to social mirroring remains unclear. Yawning may serve multiple functions or may be an evolutionary vestige whose original purpose is obscured by time. Our sense of direction, which feels reliable, contains systematic flaws. When walking without external landmarks, such as through a featureless landscape or in darkness, people inevitably begin to walk in circles rather than maintaining a straight line. This has been documented repeatedly, with lost hikers and experimental subjects alike showing the tendency. The cause appears to be small asymmetries in the vestibular system, the inner ear structures that detect motion and orientation. Tiny differences between left and right vestibular inputs, differences so small that we cannot consciously perceive them, accumulate over time, causing gradual drift in one direction. Without visual landmarks to correct this drift, the error compounds until the person completes a circle, sometimes returning almost exactly to their starting point without realizing it. This vulnerability reveals the limitations of our internal navigation systems and explains why becoming lost without landmarks is so easy despite our confidence in our sense of direction. Some reflexes connect stimuli to responses in ways that seem arbitrary. ACHOO syndrome, or photic sneeze reflex, causes some people to sneeze when exposed to bright light, particularly when moving from darkness into sunlight. The phenomenon affects roughly 20 to 30% of people and is clearly genetic, running in families. But why would bright light trigger sneezing? The reflex involves a cross-wiring in the nervous system, where signals from the optic nerve somehow activate the trigeminal nerve, which controls sensations in the face and triggers the sneeze reflex. But the precise neural pathway and the reason this cross-wiring exists remain unclear. It provides no obvious benefit and could even be disadvantageous, causing sneezing at inopportune moments. ACHOO syndrome is one of many examples where the human body contains seemingly pointless quirks, reflexes, and connections that persist not because they serve a purpose, but because they do not harm us enough for evolution to eliminate them. Human sexuality, despite being fundamental to our existence, contains areas of surprising ignorance. The existence and nature of the G-spot, a purported erogenous zone on the anterior wall of the vagina, has been debated for decades. Some women report heightened sensitivity in this area, while others do not. Anatomical studies have produced conflicting results, with some researchers identifying distinct structures or tissue differences in the region and others finding nothing unusual. The debate is complicated by individual anatomical variation, by the difficulty of conducting rigorous studies on subjective sexual experience, and by the charged cultural context surrounding female sexuality. Some researchers argue that the G-spot is an extension of the clitoris, whose internal structures are larger and more extensive than commonly depicted. Others suggest it may be related to the urethral sponge or other pelvic tissues. The controversy highlights how even basic human anatomy can remain disputed when it involves sensitive topics and individual variation. The largest animals on Earth, blue whales, live their entire lives in the ocean, and despite decades of research, no one has ever directly observed them mating or giving birth. We know blue whales reproduce, obviously, as evidenced by the presence of calves. We can infer aspects of their reproductive biology from anatomy and from observations of pregnant females and newborns. But the actual acts of mating and birth have never been witnessed by scientists. Blue whales are solitary or found in small groups. They spend much of their time at depth or in remote ocean regions, and they do not advertise their most intimate moments. The vastness of the ocean and the difficulty of being in the right place at the right time have kept these fundamental aspects of blue whale biology hidden. It is a humbling reminder that even for species we study intensively, even for the largest animals ever to exist, there are basic behaviors that remain unseen. Perhaps no mystery of the brain is more fundamental than the question of where memories are stored. When you remember a childhood event, a fact you learned in school, or what you ate for breakfast, where in your brain is that information located? The question seems simple, but the answer is not. Early researchers hoped to find discrete memory traces, engrams, specific locations where individual memories are encoded. But decades of searching have revealed that memory is distributed. Different aspects of a single memory, the visual components, the emotional tone, the factual details, are stored in different brain regions. The hippocampus plays a crucial role in forming new memories and retrieving them, but it does not appear to be where long-term memories are permanently stored. Memories seem to involve patterns of connectivity between neurons, strengthened synapses that make certain patterns of neural activity more likely to recur. But identifying the specific physical substrate of a particular memory remains impossible with current techniques. We cannot point to a cluster of neurons and say, "There is your memory of your 10th birthday." Memory appears to be an emergent property of neural network dynamics rather than something stored in a specific location, which makes it both more robust, because it cannot be erased by localized damage, and more mysterious, because we lack a clear physical account of what memory is made of. The brain's ability to reorganize itself, neuroplasticity, is well established. After injury, the brain can sometimes compensate by having other regions take over lost functions. Learning new skills involves forming new neural connections and strengthening existing ones. But neuroplasticity varies in ways we cannot fully predict. Some individuals recover remarkably well from brain injuries that would seem devastating, while others show minimal recovery from apparently similar damage. Some brain regions are highly plastic throughout life, while others show limited capacity for change after critical developmental periods. Age affects plasticity, with children generally showing greater ability to recover from brain injury than adults, but the decline is not uniform across individuals or brain regions. Why some brains are more plastic than others, what genetic or environmental factors enhance or limit plasticity, and how we might promote greater plasticity to aid recovery from injury or enhance learning all remain active research questions without complete answers. The brain constantly evaluates options, weighing potential rewards against the effort required to obtain them. This cost-benefit analysis underlies every decision, from whether to get up for a snack to whether to pursue a demanding career. But how the brain performs this calculation remains unclear. Different neural systems process reward value and effort cost, and these systems must somehow integrate their information to guide behavior. The dopamine system, which responds to rewarding stimuli, interacts with motor systems and prefrontal regions involved in planning and decision-making. But the precise neural computations, the algorithms the brain uses to combine effort and value into a single decision variable, are not fully understood. Moreover, individuals differ in how they weight effort versus reward, with some people highly motivated by potential gains and willing to work hard, while others are more effort-averse. These individual differences likely reflect variations in neural circuitry and neurochemistry, but mapping those variations and understanding how they produce different behavioral tendencies remains a challenge. Human cognition is not merely reactive but creative, capable of generating novel ideas, imagining scenarios that have never occurred, and solving problems in innovative ways. This flexible, generative aspect of thought is what allows us to write stories, invent technologies, and adapt to new situations. But we lack clear computational models of how this works. Artificial intelligence systems can perform specific tasks with superhuman efficiency, but they struggle with the kind of open-ended, flexible reasoning that humans find natural. What allows the brain to recombine concepts in new ways, to see analogies, to imagine counterfactuals? Creativity seems to involve the ability to activate and connect disparate pieces of knowledge, to temporarily relax constraints, and to generate variations on existing patterns. But the neural basis of these processes is poorly understood. Studies using brain imaging show that creative thinking involves widespread activation across many brain regions, including areas involved in memory, attention, and executive control, but these observations do not yet constitute an explanation. Building artificial systems that can match human creativity or understanding the neural algorithms underlying flexible cognition remain frontiers where observation far outpaces theory. These mysteries of body and mind, from the mundane to the profound, remind us that understanding ourselves is an ongoing project, never complete, always revealing new depths. The body we inhabit performs countless functions we do not consciously control and cannot fully explain. The brain generates our inner world of thought and feeling through mechanisms we are only beginning to glimpse. Each answer raises new questions. Each explanation reveals new complexity beneath. And so we continue to investigate, measure, theorize, seeking to understand the biological substrate of our existence and the nature of the consciousness that contemplates its own origins. When we turn inward to examine the nature of consciousness itself, we confront what may be the deepest mysteries of all. The human mind is the lens through which we perceive and understand everything, yet the mind itself remains profoundly puzzling. How does the physical brain, a 3-pound mass of cells and chemicals, give rise to the subjective experience of being someone, of seeing colors, feeling emotions, making choices? These questions have occupied philosophers for millennia and neuroscientists for decades, yet they persist with a stubbornness that suggests we may be missing something fundamental in our approach. Consciousness is not simply difficult to explain, but seems to resist explanation in ways that other biological phenomena do not. We can trace the chemistry of digestion, map the circuits of vision, decode the signals that control movement, but when it comes to explaining why there is something it is like to be conscious, why experience has a felt quality, our scientific frameworks seem inadequate. One of the most basic puzzles concerns how we experience a unified, coherent world when the brain processes information in a massively distributed fashion. This is known as the binding problem. When you look at a red apple, different aspects of that perception are processed in different brain regions. The shape is analyzed in one area, the color in another, the motion if the apple is moving in yet another region. Your knowledge about what apples are, memories of eating apples, the word apple, all of these involve additional separate brain areas. Yet you do not experience these as separate fragments. You experience a single, unified perception of an apple. How does the brain bind all these distributed pieces of information into a coherent whole? Various proposals have been made. Perhaps neurons that code for different aspects of the same object fire in synchrony, their coordinated timing serving as a tag that links them together. Perhaps there are convergence zones where information from different processing streams comes together. Perhaps attention acts as a binding mechanism, selecting and integrating relevant information. But none of these explanations is entirely satisfying, and the binding problem persists. It is not just an academic puzzle, but touches on the fundamental question of how the brain creates the seamless, integrated experience of consciousness from the fragmented, parallel processing that neuroscience reveals. Closely related is the mystery of self-awareness, the sense of being a unified self that persists through time, that has thoughts and feelings and makes decisions. We feel ourselves to be coherent entities, yet when we look for the self in the brain, we find no single structure that corresponds to it. Self-awareness involves many brain regions, including parts of the prefrontal cortex, the posterior cingulate, the insula, and regions collectively called the default mode network that activate when we think about ourselves. But damage to any one of these areas does not eliminate self-awareness, and possessing these structures does not seem sufficient to guarantee it. The self appears to be an emergent property, something that arises from the interaction of multiple systems rather than residing in any particular location. But what kind of emergence is this? How do neurons and synapses, which individually have no awareness, collectively generate the feeling of being someone? We can describe the brain activity correlated with self-awareness, but correlation is not explanation. The gap between describing what the brain does when we are self-aware and explaining how brain activity produces the subjective feeling of selfhood remains vast. This gap is the essence of what philosopher David Chalmers called the hard problem of consciousness. The hard problem is not about explaining how the brain processes information, how it discriminates stimuli, how it integrates information and produces reports about mental states. These are the easy problems, not because they are trivial but because they seem amenable to standard neuroscientific methods. The hard problem is explaining why all this processing is accompanied by subjective experience, why there is something it feels like to see red, to feel pain, to taste chocolate. Even if we had a complete map of the brain and understood every neural circuit perfectly, Would that explain why consciousness exists at all? Why could not all this information processing happen in the dark, without any inner experience? The hard problem suggests that there may be an explanatory gap between physical processes and subjective experience that cannot be bridged by accumulating more neuroscientific data. Some philosophers and scientists argue that consciousness is a fundamental feature of the universe, not reducible to physical processes, while others maintain that consciousness will eventually be explained once we understand the brain well enough. But currently, we have no theory that satisfactorily explains why subjective experience exists. Some researchers have proposed that quantum mechanics might play a role in consciousness, that quantum effects in the brain could explain aspects of conscious experience or even provide a physical basis for phenomena like free will. The idea is intriguing because quantum mechanics introduces genuine indeterminacy and non-classical behavior that might seem relevant to consciousness. But quantum effects in biological systems are controversial. The brain is warm and wet, conditions that generally cause quantum coherence to collapse almost instantly through a process called decoherence. For quantum effects to be relevant to consciousness, there would need to be structures in the brain that can maintain quantum states long enough to influence neural processing. Some researchers have proposed that microtubules, structural proteins inside neurons, might support quantum processes, but this remains highly speculative and unproven. Most neuroscientists are skeptical that quantum mechanics is necessary to explain brain function, believing that classical physics and chemistry are sufficient. The question remains open but highly contentious, with no experimental evidence yet demonstrating that quantum effects play a functional role in consciousness. At a more tractable level, we still lack complete understanding of how the brain integrates information from different senses. When you watch someone speak, you integrate the visual information of their moving lips with the auditory information of their voice, and this integration is so seamless that it affects what you hear. If the visual and auditory signals are mismatched, as in the McGurk effect, you can actually hear different sounds than what was spoken. This multisensory integration happens throughout the brain, in early sensory areas and in higher association regions. But the rules governing how the brain decides to integrate information from different senses, how it weights conflicting cues, and how it maintains calibration between sensory modalities are incompletely understood. Different sensory systems have different processing speeds and different spatial and temporal resolutions, yet the brain produces a unified percept. The computational principles and neural mechanisms underlying this integration remain an active area of research. Memory consolidation, the process by which short-term memories are transformed into stable long-term memories, involves changes at synapses, the connections between neurons. Specific synapses are somehow tagged during learning so that they are selectively strengthened during consolidation. But the molecular identity of these synaptic tags remains unknown. Various candidate molecules have been proposed, and we know that protein synthesis is required for long-term memory formation, but identifying the specific tagging molecules and understanding exactly how they work to mark particular synapses for strengthening is an unsolved problem. Without knowing what the tags are, our understanding of memory consolidation remains incomplete. Language, one of humanity's defining features, involves complex neural networks distributed across the brain. Classical models identified Broca's area in the frontal lobe as important for speech production and grammatical processing, and Wernicke's area in the temporal lobe as important for comprehension. But modern brain imaging reveals a much more complex picture, with many regions involved in different aspects of language. The neural circuits that handle syntax, the grammatical structure of sentences, and semantics the meaning of words and sentences are not fully mapped. These systems clearly interact but also show some independence, as evidenced by patients who have deficits in one aspect of language but not others. How syntax and semantics are represented in the brain, how they are processed, and how they are integrated during comprehension and production remain areas of active investigation without consensus answers. The ease and speed with which children acquire language has led some linguists, notably Noam Chomsky, to propose that humans have an innate language acquisition device, a specialized cognitive module dedicated to learning language. This would explain why children can learn complex grammatical structures from limited and sometimes imperfect input, why all human languages share certain deep structural similarities, and why language acquisition follows similar developmental patterns across cultures. But the existence of such a device remains debated. Some researchers argue that general learning mechanisms, not language-specific ones, can account for language acquisition, that children's powerful pattern recognition and statistical learning abilities are sufficient. Brain imaging has not revealed any single structure that could be identified as the language acquisition device, and attempts to find genes specifically for language have had limited success. The debate touches on fundamental questions about human nature, whether we are born with specialized cognitive machinery or with general-purpose learning systems that adapt to any task. The question of whether the language we speak shapes how we think, known as linguistic relativity or the Sapir-Whorf hypothesis, has fascinated and divided researchers. Different languages carve up the world differently, with different systems for describing space, time, color, kinship, and countless other domains. Does speaking a language that has many words for snow make you perceive snow differently than someone whose language has only one word? Does speaking a language that uses absolute directions rather than relative ones, saying the cup is north of the plate rather than the cup is to the right of the plate, change how you mentally represent space? Some studies have found evidence for subtle effects of language on cognition, but the effects are often inconsistent across different tasks and populations. Strong versions of linguistic relativity, claiming that language fundamentally determines thought, are generally rejected, but weak versions suggesting that language can influence certain aspects of cognition remain plausible. The difficulty is separating language from culture, experience, and other factors that also shape cognition, making it hard to isolate the specific effect of linguistic structure. Perhaps no question is more central to our sense of ourselves than whether we have free will, whether our choices are truly ours or whether they are determined by prior causes, by brain states we did not choose. Neuroscience has revealed that conscious awareness of a decision often comes after brain activity predicting that decision has already begun, suggesting that what we experience as conscious choice may be a retrospective narrative the brain constructs rather than the actual cause of action. But interpreting these findings is contentious. Some argue they demonstrate that free will is an illusion, that our choices are determined by unconscious brain processes and prior causes. Others argue that even if our decisions are caused by brain activity, they can still be free as long as they reflect our desires, values, and reasoning processes. Still others suggest that the question is poorly framed, that free will and determinism are not necessarily incompatible, or that neither concept adequately captures the complexity of human decision-making. We lack a coherent neuroscientific model that can explain how causes at the neural level relate to the experience of making choices at the subjective level. The free will debate remains unresolved, tangled in questions about causation, consciousness, and what it means to be an agent. These mysteries of mind and consciousness represent the frontier where science meets its deepest challenges. They are not merely technical problems awaiting better instruments or more data, but conceptual puzzles that may require new frameworks for thinking about the relationship between matter and experience, between brain and mind. Each mystery points to the limits of our current understanding, to questions that resist our standard methods of inquiry. Yet these are also the questions that define what it means to be human, to be conscious, to wonder about our own nature. And so we continue to probe, knowing that the answers, if they come, may transform not just neuroscience but our understanding of ourselves. Among the most universal experiences of living things is sleep, yet its fundamental purpose remains one of biology's enduring mysteries. Nearly all animals sleep in some form, from jellyfish to birds to humans, suggesting that sleep fulfills a crucial biological function. We spend roughly a third of our lives unconscious and vulnerable, which seems like a dangerous strategy unless sleep provides benefits that outweigh the risks. But what exactly does sleep do that cannot be accomplished while awake? Numerous theories have been proposed. Sleep may be essential for memory consolidation, transferring information from temporary storage to long-term memory and integrating new experiences with existing knowledge. Sleep may allow the brain to clear metabolic waste products that accumulate during waking hours, with recent research showing that the brain's waste clearance system operates more efficiently during sleep. Sleep may be necessary for synaptic homeostasis, downscaling the connections between neurons that have been strengthened during the day to prevent the brain from becoming oversaturated. Sleep deprivation has severe consequences, impairing cognition, mood, immune function, and metabolism, and prolonged sleep deprivation is eventually fatal. Yet no single function fully explains why sleep is necessary, why it takes the specific form it does with alternating cycles of deep and light sleep, or why different species sleep for vastly different durations. Some animals sleep for hours each day while others seem to manage with only minutes. The diversity of sleep patterns across species suggests that sleep may serve multiple functions, with different aspects being more or less important depending on an organism's ecology and physiology. Dreams, those strange narratives that unfold during sleep, add another layer of mystery. Most vivid dreaming occurs during REM sleep, when the brain is highly active but the body is paralyzed. Dreams can be bizarre, emotional, terrifying, or mundane, pulling fragments from memory and weaving them into scenarios that often make little sense upon waking. But what generates dreams? And why do they have the particular qualities they do? Some theories suggest dreams are the brain's attempt to make sense of random neural activity during sleep, creating narratives from noise. Others propose that dreams serve a function in processing emotions, working through anxieties and fears in a safe context. Still others suggest dreams play a role in memory consolidation or problem solving, allowing the brain to explore associations and possibilities without the constraints of waking logic. But we lack a clear mechanistic understanding of how dreams are generated, which neural circuits produce the imagery and narrative, and why dream content takes the forms it does. The subjective nature of dreams makes them difficult to study objectively, and the fact that we forget most dreams upon waking leaves us with only fragmentary data about what occurs during sleep. At the most fundamental level of neuroscience, we still debate how information is encoded in the brain. Neurons communicate through electrical impulses called action potentials or spikes. But how exactly do these spikes represent information? Is it the rate of firing that matters, with more spikes per second encoding stronger signals? Is it the precise timing of individual spikes that carries information? Is it the patterns of activity across populations of neurons, with information distributed across many cells? Evidence exists for all these coding schemes, and likely the brain uses different strategies in different regions and for different types of information. But we lack a unified theory of neural coding, a comprehensive understanding of how the brain transforms sensory inputs, memories, and goals into patterns of neural activity and then back into perception, thought, and action. This gap in understanding limits our ability to interpret brain recordings and to build artificial systems that process information the way brains do. As we descend from the level of neural circuits to molecular biology, we find that quantum mechanics, that strange physics of the very small, may play unexpected roles in living systems. Quantum mechanics is typically associated with carefully controlled laboratory conditions, with isolated atoms and photons at temperatures near absolute zero. Biological systems are warm, wet, and noisy, conditions that should destroy quantum effects almost instantly. Yet in recent years, evidence has accumulated that quantum coherence, where particles exist in multiple states simultaneously, can persist in biological molecules longer than classical physics would predict. This has been observed most clearly in photosynthesis, where quantum coherence appears to help energy transfer efficiently from light-capturing pigments to reaction centers. The discovery that biological systems can maintain quantum coherence even briefly opens the possibility that evolution has learned to exploit quantum effects for functional purposes, but exactly how and where this occurs remains an area of active research and debate. Quantum effects may also accelerate chemical reactions in ways that classical chemistry cannot fully explain. Proton tunneling, where a proton passes through an energy barrier rather than over it, is a quantum mechanical phenomenon that can dramatically speed up certain reactions. In enzymatic reactions, where enzymes catalyze biochemical transformations, proton tunneling appears to play a role in some cases, allowing reactions to proceed faster than would be possible if protons had to surmount energy barriers classically. This may be particularly important at physiological temperatures where thermal energy alone is insufficient to drive certain reactions at biologically relevant rates. The extent to which enzymes have been shaped by evolution to exploit quantum tunneling and whether this represents a general principle or is limited to specific cases remains an open question. Even the stability of our genetic code may involve quantum effects. DNA bases can exist in rare tautomeric forms, alternative arrangements of atoms where a hydrogen atom shifts position. If a base is in a tautomeric form during DNA replication, it can mispair with the wrong base, causing a mutation. Classical models treat these tautomeric shifts as random thermal fluctuations, but quantum mechanical calculations suggest that proton tunneling could cause these shifts in ways that are not entirely random. If quantum effects influence mutation rates in DNA, this could have implications for understanding evolution and the origins of genetic diseases. However, demonstrating that quantum tunneling actually contributes to mutation rates in living cells, as opposed to merely being theoretically possible, is challenging, and the hypothesis remains controversial. One of the fundamental mysteries of biochemistry is homochirality, the fact that biological molecules exhibit a specific handedness. Amino acids, the building blocks of proteins, exist in two mirror-image forms called left-handed and right-hand, but life on Earth uses exclusively left-handed amino acids. Similarly, the sugars in DNA and RNA are all right-hand. This uniformity is essential for the proper functioning of biological molecules, but its origin is unexplained. In laboratory synthesis of amino acids, left and right-hand forms are produced in equal amounts, a racemic mixture. Yet somehow, early in the history of life, one-handedness was selected over the other. Various explanations have been proposed. Perhaps a small initial imbalance, caused by chance or by physical processes such as circularly polarized light, was amplified through autocatalytic reactions where molecules of one-handedness preferentially catalyze the formation of more molecules of the same handedness. Perhaps certain mineral surfaces preferentially adsorbed one-handedness, concentrating it. Perhaps homochirality arose multiple times and life with the other-handedness simply went extinct. But we have no definitive answer for why life chose the specific handedness it did or how that choice became locked in. Proteins, the workhorses of the cell, must fold into precise three-dimensional shapes to function. The sequence of amino acids determines the final structure, but how a protein navigates from an unfolded chain to its functional form is not fully understood. The classical view holds that proteins fold to the lowest energy state, the most thermodynamically stable configuration. But protein folding is complex, with an astronomical number of possible conformations to explore. If proteins sampled every possible shape, folding would take longer than the age of the universe, yet proteins fold in milliseconds to seconds. Protein folding must follow pathways, with intermediate states guiding the process. But some proteins may not fold to the absolute lowest energy state but instead to metastable states, configurations that are stable enough to function but not the most thermodynamically favorable. This could explain why some proteins can misfold and aggregate, getting trapped in alternative stable conformations. The mechanisms that guide folding, prevent misfolding, and rescue proteins that have folded incorrectly are not fully elucidated. Inside cells, the concentration of proteins and other macromolecules is extraordinarily high, creating what is called molecular crowding. The cell interior is not a dilute solution but a densely packed environment where up to 40% of the volume is occupied by macromolecules. Under such crowded conditions, we would expect proteins to collide frequently and aggregate, forming clumps that would be non-functional and potentially toxic. Yet cells maintain protein solubility and function despite this extreme crowding. How they accomplish this is not entirely clear. Molecular chaperones, proteins that assist in folding and prevent aggregation, play a crucial role, but the full repertoire of mechanisms that prevent unwanted interactions in crowded environments is still being discovered. Understanding how cells manage molecular crowding has implications for many diseases, including neurodegenerative conditions where protein aggregation is a central feature. Among the strangest infectious agents are prions, misfolded proteins that can induce other proteins of the same type to misfold, propagating the misfolding through tissues. Prions cause devastating neurodegenerative diseases such as Creutzfeldt-Jakob disease in humans, scrapie in sheep, and mad cow disease in cattle. What makes prions so remarkable and so disturbing is that they violate a central dogma of biology. They are infectious agents that contain no nucleic acids, no DNA or RNA. All other known infectious agents, from viruses to bacteria to parasites, carry genetic material that encodes their structures and enables replication. Prions replicate by inducing conformational change in normal proteins, converting them to the misfolded prion form through a templating mechanism. The prion form is stable and tends to aggregate, eventually killing cells. How a protein can carry information about its misfolded state and transmit that information to other proteins without any genetic material challenges our understanding of biological information. Prions also exhibit strains, different misfolded conformations that produce distinct disease phenotypes, further complicating the picture. The prion hypothesis was initially met with skepticism precisely because it seemed to defy fundamental principles, but extensive research has confirmed that proteins alone can be infectious. Prions remind us that biology can find pathways we do not anticipate, that the boundary between living and non-living, between information and matter, is more fluid than we assumed. These mysteries at the molecular and cellular level reveal that even the most basic processes of life contain depths we have not fully plumbed. From the nightly rhythm of sleep to the quantum processes that may occur in molecules, from the origin of molecular handedness to the strange behavior of infectious proteins, we find that life operates through mechanisms that are intricate, sometimes counterintuitive, and not yet completely understood. Each discovery seems to raise as many questions as it answers. Each phenomenon we explain reveals new layers of complexity beneath. And so the investigation continues, probing deeper into the molecular machinery of life, seeking to understand the principles that govern the most fundamental processes of living systems. The world of chemistry, for all its success in understanding and manipulating matter, still harbors fundamental challenges that resist solution. These are not merely technical obstacles but puzzles that reveal gaps in our theoretical understanding, limits to our synthetic capabilities, and phenomena that behave in ways our models do not predict. Chemistry operates at the boundary between the quantum world of individual atoms and the macroscopic world we experience, and in that boundary region, surprises persist. Some reactions that should be simple prove maddeningly difficult. Some structures that theory predicts should exist cannot be made. Some processes occur faster or more efficiently than our equations suggest they should. These mysteries remind us that chemistry, despite its rigorous mathematical foundations and centuries of accumulated knowledge, still contains territory that is unmapped. One of the most sought-after goals in organic chemistry is the development of universal chiral catalysts that can reliably produce molecules with a specific handedness regardless of the substrate. Chirality, the property of handedness in molecules, is crucial in drug development because mirror image forms of a molecule can have dramatically different effects in the body. Many catalysts have been developed that work beautifully for specific reactions or classes of molecules, but a truly universal catalyst, one that could handle any organic transformation with high selectivity, remains elusive. The challenge lies in the diversity of organic chemistry. Different functional groups, different steric environments, different electronic properties all influence how a catalyst interacts with a substrate. What works for one class of molecules may fail completely for another. Chemists have made remarkable progress in asymmetric catalysis, developing sophisticated chiral ligands and catalysts for many important transformations, but the dream of universality, of a single catalyst or family of catalysts that could address any stereochemical problem, has not been realized and may not be achievable given the fundamental diversity of chemical structures and reactions. A related synthetic challenge involves creating quaternary carbon centers with specific stereochemistry. A quaternary carbon is one bonded to 4 other carbon atoms, and when these 4 substituents are all different, the quaternary center is chiral. Building such centers with control over which enantiomer forms is remarkably difficult. The steric crowding around a quaternary carbon makes reactions sluggish, and controlling the approach of reagents to create a specific 3-dimensional arrangement is challenging. While methods exist for certain cases, general, efficient approaches remain limited. This synthetic difficulty constrains the types of molecules chemists can reliably make, which in turn limits drug discovery and material science where complex molecular architectures are desired. Nature creates complex molecules with remarkable efficiency using enzymes, proteins that catalyze reactions with exquisite specificity and speed. Chemists have long tried to create artificial enzymes, synthetic molecules that could mimic the catalytic power of natural enzymes. Progress has been made, with designed molecules and even artificial proteins showing catalytic activity. But artificial enzymes generally require protecting groups, chemical modifications that temporarily block certain reactive sites on a molecule to prevent unwanted reactions. Natural enzymes rarely need such protections, operating on substrates in their natural forms through precise positioning and tailored microenvironments within the enzyme's active site. The fact that artificial systems still require protecting groups indicates that we have not yet fully captured the principles that make natural enzymes so effective. We can mimic their activity in limited ways, but replicating their elegance and generality remains beyond our reach. Electrochemistry, using electrical current to drive chemical reactions, offers an environmentally friendly alternative to traditional reagents, but electrochemical organic reactions face significant challenges. Many organic molecules are unstable under the conditions required for electrochemical reactions, breaking down or forming unwanted products. Controlling selectivity in electrochemical reactions, ensuring that the desired transformation occurs rather than competing side reactions, is difficult. The electrode surface, where reactions occur, can become passivated or fouled, losing activity over time. Despite these challenges, electrochemistry holds great promise for green chemistry, and active research seeks to overcome these limitations and expand the repertoire of reactions that can be performed electrochemically. Some reactions occur faster at interfaces between water and organic solvents than they do in either phase alone, a phenomenon that defies standard chemical kinetics. Normally, we expect reaction rates to depend on the concentration of reactants and the activation energy of the reaction. But at water-organic interfaces, molecules can become oriented or concentrated in ways that dramatically accelerate reactions. The precise mechanisms are not fully understood, but the interface appears to provide a unique environment where molecules are positioned favorably for reaction and where the properties of the two solvents combine to stabilize transition states. This has implications for understanding reactions in biological systems, where interfaces between aqueous and lipid phases are ubiquitous, and for developing new synthetic methods that exploit interfacial chemistry. Theoretical chemistry occasionally predicts structures or bonding types that have never been observed experimentally. One such prediction is the phi bond, a type of chemical bond where four lobes of electron density would overlap between atoms, creating a bond with different symmetry than the familiar sigma and pi bonds. Calculations suggest that phi bonds could exist in certain heavy element compounds, but no one has successfully synthesized a molecule with a confirmed phi bond. The absence might be because the conditions required are too extreme, or because competing bonding arrangements are always more stable, or because the molecules that could exhibit phi bonding are inherently unstable. The phi bond remains a theoretical curiosity, a reminder that not everything predicted by quantum chemistry can be realized in a test tube. Similarly, nitrogen allotropes beyond the familiar diatomic nitrogen gas have been theorized. Nitrogen should, in principle, be able to form polymeric structures similar to those of its neighbor carbon, which forms graphite, diamond, and numerous other allotropes. Polymeric nitrogen would be an extremely high-energy material, potentially useful as a propellant or explosive. But all attempts to synthesize stable nitrogen allotropes have failed. Under extreme pressure, nitrogen can be forced into different structures, but these revert to diatomic nitrogen when pressure is released. The reluctance of nitrogen to form anything but N2 molecules reflects the extraordinary stability of the nitrogen-nitrogen triple bond, one of the strongest bonds in chemistry. Breaking these bonds and convincing nitrogen atoms to form different bonding arrangements stable at normal conditions has proven impossible. The difficulty highlights how atomic properties constrain the forms matter can take, regardless of theoretical possibilities. Enzymes catalyze reactions with extraordinary speed, but some enzymes appear to operate even faster than diffusion should allow. Diffusion limits how quickly molecules can encounter each other in solution, setting an upper bound on reaction rates. Yet certain enzymes, particularly those involved in critical metabolic pathways, catalyze reactions at rates that approach or even seem to exceed this diffusion limit. How is this possible? Various mechanisms have been proposed. Perhaps enzymes create electric fields or use other forces to guide substrates toward their active sites, effectively pulling molecules in faster than random diffusion would deliver them. Perhaps substrates do not fully leave the enzyme between turnovers, remaining loosely associated and available for immediate recatalysis. Perhaps enzyme motions channel products away efficiently, preventing them from blocking the active site. The phenomenon suggests that enzymes are even more sophisticated than we realized, not merely passive structures waiting for substrates to arrive but active participants in substrate recruitment and product release. Sometimes, ancient technologies present mysteries that modern science struggles to explain. The Iron Pillar of Delhi, erected around 400 CE, stands over 7 meters tall and weighs more than 6 tons. What makes it remarkable is its resistance to corrosion. While iron typically rusts rapidly in humid environments, this pillar has stood for over 1600 years with minimal rust. Various explanations have been proposed for its durability. The iron used is exceptionally pure, with low sulfur and high phosphorus content. The phosphorus may have formed a protective coating on the surface, a layer of mica white that prevents deeper corrosion. The pillar's mass and surface area to volume ratio may help it remain dry, shedding moisture before corrosion can proceed. Traditional metalworking techniques may have produced an iron with unusual microstructure. But no single explanation fully accounts for the pillar's longevity, and attempts to replicate its corrosion resistance using similar materials and techniques have had limited success. The iron pillar stands as a testament to ancient metallurgical skill and as a reminder that practical knowledge can sometimes exceed theoretical understanding, that craftsmen can achieve results that scientists struggle to explain or reproduce. These mysteries scattered across chemistry, from the frustrations of synthesis to the anomalies of reaction kinetics to the enigmas of ancient artifacts, illustrate the incompleteness of our mastery over matter. Chemistry gives us tremendous power to transform substances, to create materials and medicines that reshape the world. Yet this power comes with limitations, with reactions we cannot perform, structures we cannot build, phenomena we cannot predict or control. Each limitation points to gaps in understanding, to principles not yet grasped or complexities not yet unraveled. And each mystery invites investigation, promising that deeper understanding awaits those who persist in asking why chemistry behaves the way it does, why some things that should work do not, and why some things work for reasons we cannot yet explain. Mathematics occupies a unique place among the sciences, existing in a realm of pure logic and abstraction, yet somehow describing the physical world with uncanny precision. The equations of physics, the patterns of nature, the structures of chemistry all find expression in mathematical language. Yet mathematics itself contains profound mysteries, questions that have resisted the efforts of the finest minds for decades or even centuries. These are not mysteries about the physical world but about the nature of numbers, shapes, and logical structures themselves. Some of these problems seem almost trivial to state, describable in a few sentences that anyone can understand, yet their solutions remain tantalizingly out of reach. Others involve concepts so abstract that only specialists can fully grasp what is being asked. Together, they form a landscape of unsolved problems that reveals the limits of human understanding even in the most rigorous and logical of disciplines. Perhaps no problem better exemplifies this than the Riemann hypothesis, formulated in 1859 by the German mathematician Bernhard Riemann. The hypothesis concerns the distribution of prime numbers, those numbers divisible only by themselves and 1. Primes appear to be scattered irregularly among the integers, yet there are patterns in their distribution. Riemann discovered a deep connection between the primes and a complex function called the zeta function. The Riemann hypothesis states that all non-trivial zeros of the zeta function lie on a specific line in the complex plane, the line where the real part equals 1/2. If true, it would provide profound insights into the distribution of primes and connect to countless other areas of mathematics. The hypothesis has been tested numerically for trillions of zeros, and every single one found lies exactly where Riemann predicted. The evidence is overwhelming, yet evidence is not proof. Mathematics requires absolute certainty, and despite a century and a half of effort, no one has been able to prove the Riemann hypothesis. Its truth seems almost certain, yet certainty without proof is unsatisfying, a gap between what we believe and what we can demonstrate. Another profound question concerns the fundamental limits of computation. Some problems can be solved quickly by computers, with the time required growing as a polynomial function of the problem size. These are called p-problems. Other problems can be verified quickly if someone gives you a solution, but finding the solution in the first place seems to require trying exponentially many possibilities. These are called NP problems. The P versus NP question asks whether every problem whose solution can be verified quickly can also be solved quickly. Most computer scientists believe the answer is no, that P does not equal NP, meaning there exist problems that are fundamentally harder to solve than to verify. But proving this has resisted all attempts. The question has profound implications. If P equals NP, many problems thought to be computationally intractable, including breaking most modern encryption, would become solvable efficiently, revolutionizing computer science and threatening digital security. If P does not equal NP, as most suspect, it means there are inherent limits to what computers can efficiently accomplish, boundaries beyond which problems remain forever out of reach of fast algorithms. The P versus NP problem is not just about computers but about the nature of mathematical proof itself, about whether finding solutions is fundamentally harder than checking them. The Navier-Stokes equations, which describe the motion of fluids, are central to physics and engineering. They govern everything from airflow over wings to weather patterns to ocean currents. Yet we do not know whether smooth solutions to these equations always exist or whether they can develop singularities, points where velocities become infinite in finite time. This is the Navier-Stokes existence and smoothness problem, one of the Clay Mathematics Institute's Millennium Prize problems. In 3 dimensions, we cannot prove that given reasonable initial conditions, the equations will always produce a solution that remains smooth and well-behaved for all time. It is possible that under certain conditions, the flow could develop infinitely sharp features, breaking down the mathematical framework. This uncertainty reflects a gap between our physical intuition, which suggests fluids should behave smoothly, and our mathematical understanding, which cannot guarantee it. The problem touches on the nature of turbulence and the fundamental limits of predictability in fluid systems. Elliptic curves, geometric objects described by certain polynomial equations, have deep connections to number theory. The Birch and Swinnerton-Dyer conjecture relates the number of rational points on an elliptic curve to the behavior of an associated function called an L function. Specifically, it predicts that if the L function has a zero at a certain point, the elliptic curve has infinitely many rational points, and the order of that zero relates to the structure of those points. The conjecture has been verified for many specific elliptic curves and is believed to be true in general, but a proof remains elusive. The conjecture is important not just for its own sake, but because it reveals deep connections between seemingly disparate areas of mathematics, linking geometry, analysis, and number theory in unexpected ways. The Hodge conjecture concerns the geometry of higher dimensional spaces and the question of which geometric features can be represented algebraically. In technical terms, it asks whether certain cohomology classes on algebraic varieties can be represented by algebraic cycles. The conjecture has been proven in some special cases but remains open in general. It sits at the intersection of algebraic geometry and topology, probing the relationship between continuous geometric properties and discrete algebraic structures. The difficulty of the problem reflects the deep subtlety of higher dimensional geometry, where intuition from familiar three-dimensional space often fails. Sometimes the most frustrating mathematical problems are those with the simplest statements. The Collatz conjecture is a perfect example. Start with any positive integer. If it is even, divide it by 2. If it is odd, multiply by 3 and add 1. Repeat this process. The conjecture states that no matter what number you start with, you will eventually reach the number 1. This can be explained to a child, yet no one has been able to prove it. Computers have tested the conjecture for enormous numbers, and it holds in every case, but a general proof remains out of reach. The problem is deceptive because the rule is so simple, yet the behavior of the sequence is chaotic and unpredictable. The Collatz conjecture resists standard mathematical techniques, and many mathematicians believe it may be undecidable, impossible to prove or disprove within standard mathematical frameworks. The twin prime conjecture is another simply stated but profoundly difficult problem. Twin primes are pairs of prime numbers that differ by 2, like 3 and 5, or 11 and 13. The conjecture states that there are infinitely many such pairs. Primes become rarer as numbers get larger, yet twin primes continue to appear even among very large numbers. Recent progress has shown that there are infinitely many pairs of primes with gaps of bounded size, getting closer to the twin prime conjecture but not quite reaching it. The gap between what has been proven and what is conjectured illustrates how even slight variations in a problem can move it from solved to unsolved, from accessible to intractable. Graph theory, the study of networks of connected points, contains its own collection of unsolved problems. Hadwiger's conjecture concerns graph coloring, the problem of assigning colors to the vertices of a graph so that no two connected vertices share the same color. The conjecture relates the minimum number of colors needed to a structural property of the graph called its clique minor. It generalizes the famous four-color theorem, which states that any map can be colored with 4 colors so that no adjacent regions share a color. Hadwiger's conjecture has been proven for small numbers of colors but remains open in general. The difficulty lies in the complexity of graph structures and the subtle ways that coloring properties relate to underlying topological features. Jaeger's Peterson coloring conjecture deals with a different aspect of graph coloring, concerning edge colorings of certain types of graphs. The conjecture proposes that every bridgeless graph with sufficient connectivity has an edge coloring with specific properties related to the Peterson graph, a particular graph with interesting symmetries. Like many graph theory conjectures, it has been verified for special cases but remains unproven in full generality. The persistence of these problems despite decades of effort by graph theorists indicates that our understanding of network structures, for all its sophistication, still contains significant gaps. These mathematical mysteries, from the distribution of primes to the behavior of fluids to the properties of graphs, share a common feature. They concern objects and relationships that can be precisely defined, explored computationally, and tested against examples, yet they resist complete understanding. Mathematics, which we often imagine as a realm of certainty and proof, turns out to contain vast territories where certainty eludes us, where conjectures supported by mountains of evidence nonetheless remain conjectures because the final step to proof cannot be taken. These problems are not merely technical challenges but windows into the structure of mathematical reality, hints that even in the most abstract and logical of domains, there are depths we have not yet fathomed. They remind us that understanding, even in mathematics, is a process without a clear endpoint, that each proof generates new questions, and that the landscape of the unknown extends far beyond what we can currently see. In this way, mathematics mirrors the uncertainty and mystery that pervades every other domain of human inquiry, proving that the unknown is not a temporary condition waiting to be eliminated but a permanent feature of the relationship between mind and reality.